The galaxy appears as a
quiet
barred spiral with a
geometry
bright
of a
central
spiral.
bulge, a wide star-filled disk, and an extended halo that
Where
faintly
density
encloses the system.
becomes light.
Stars, dust, and gas arrange into curved lanes that circle the center under gravity and rotation. The disk is not uniform. Density rises along spiral patterns where material crowds together and falls in the regions between. In these denser arcs, the interstellar medium cools, clouds condense, and young clusters begin to form. Farther from the arcs, the density is lower, yet older stars continue to orbit and provide a steady background that records the long history of the disk. The central bulge stands above the plane of the disk and hosts a supermassive black hole that sets the deepest part of the gravitational well. Across the inner disk, a bar-shaped arrangement of stars channels gas along its length. The bar turns as a pattern more slowly than individual stars and clouds. Where the differing speeds of bar and disk establish resonances, gas is guided into rings and lanes. These rings concentrate material and support elevated rates of star formation over long intervals. The result is an inner region that reorganizes itself through a combination of rotation, pressure forces, and gravity, with gas continually redistributed toward favored orbits. Spiral arms act as traveling density waves rather than fixed structures. Stars and gas enter slow relative to the wave and experience compression.
Fields prevail.
Compression lowers temperature, increases density, and encourages the formation of molecular clouds. Within those clouds, gravity overcomes internal support and cause collapse into protostars. Massive stars that form in these settings emit strong ultraviolet radiation and drive powerful winds. Their radiation ionizes surrounding gas, and their winds and later explosions stir the medium and enrich it with heavier elements. The arms therefore help regulate both the rate of star formation and the chemical makeup of future generations of stars. The interstellar medium consists of distinct phases that interpenetrate and exchange energy and matter. Along the mid-plane, cold molecular gas collects into filaments and clumps that reach high densities. A thicker layer of warmer neutral hydrogen extends above and below the mid-plane. Hot ionized gas occupies a still thicker layer and fills bubbles and chimneys left by clusters of massive stars. Above the disk, a warm, diffuse halo contains gas that circulates on longer timescales. Magnetic fields thread all phases and couple to charged particles, influencing turbulence, guiding flows, and supporting gas against gravity where thermal pressure alone is not sufficient. Cosmic rays contribute additional pressure and help shape the balance among phases. The rotation curve of the galaxy remains high well beyond the luminous disk. The most straightforward interpretation is that a large halo of dark matter outweighs stars and gas and holds outer orbits in place. Within this wider halo, the disk is not perfectly flat. It is warped and flared with the mid-plane bending, and the thickness of the gas layer increasing with radius. The warp changes how lines of sight intersect the layers of dust and gas, and the flare alters the height distribution of the material. These large-scale features, combined with the bar and spiral arms, define the paths along which gas moves and collects. Radiation fields vary strongly across the disk. Near young clusters, ultraviolet light is intense and forms extended ionized regions. Farther away, where the radiation field is softer, gas stays neutral or molecular. Dust grains absorb starlight and re-emit it in infrared wavelengths, carrying heat away from dense clouds, while also shielding interiors from radiation. Turbulence driven by differential rotation, stellar feedback and magnetic processes maintains a broad range of densities and temperatures. This turbulence both supports clouds and seeds density contrasts that can grow under gravity. The interplay of radiation, turbulence, magnetic fields and gravity sets the conditions for where and when stars form. The portion of the sky identified as Cygnus presents a long sight line through the disk. The view crosses multiple arm segments and passes through several known associations of massive stars. The field is crowded because the sightline lies close to the midplane, and dust lanes reduce transparency in patches, creating complex patterns of dimming and reddening. Emission from ionized gas outlines the boundaries where radiation meets denser material. Radio surveys map neutral hydrogen and reveal streaming motions and expanding shells. Millimeter observations detect molecules that trace cold cloud structures. Infrared observations penetrate dust to show embedded young stars. Together, these windows record a layered cross-section of the disk along this direction. Stars carry the imprint of their birth environments in their chemical abundances.
The dust acts
Ratios
as a
of
filter,
heavy elements,
scattering the
often
blue
summarized
starlight
as
and allowing the warmer
metallicity,
tones to dominate,
trace past
causing the
cycles of star formation and enrichment. Gradients in metallicity run from higher values nearer the center to lower values toward the outskirts. Radial migration, in which stars change their guiding centers through resonant interactions, blurs these gradients over time. Open clusters disperse as they orbit in the gravitational field of the disk, and as they experience encounters with massive clouds. The net result is a mixed stellar background in almost any direction, with populations that formed at different radii and time superimposed along the same line of sight. Gas flows along arms and across interarm regions. Feedback from massive stars creates cavities and shells that expand into the surrounding medium. When these shells merge, they form superbubbles that open channels through which hot gas reaches higher layers. Cooling then proceeds into the halo, and clouds fall back toward the plane in a slow circulation, often described as a galactic fountain. Spiral density waves and the bar transfer angular momentum allow gas to drift radially. Over many rotations, these combined processes maintain a balance so that the disk neither uses its gas all at once nor remains entirely quiescent. Astronomers construct a framework to make this complex field legible. Positions on the sky are measured by galactic longitude and latitude, and by reference to constellations. Distances are determined by parallax for nearby bright stars and by standard candles and kinematic methods for more distant structures. Spectroscopy provides radial velocities and chemical information. Polarization measurements trace magnetic field orientations. Time variability in certain sources reveals compact structures and energetic process. In crowded directions such as Cygnus, careful analysis separates overlapping layers and ties emission features to specific distances and motions. Across the disk, young clusters and associations mark recent star formation, while older field stars trace earlier episodes. In the Cygnus direction, catalogued groups of massive stars illuminate surrounding gas and produce bright ionized regions. Radio maps show filaments and arcs of neutral hydrogen that reach over large spatial scales. Millimeter mapping outlines long molecular filaments that host chains of dense clumps. Infrared imaging reveals embedded protostars within those clumps. The combined picture is a sequence in which gas collects, forms dense structures, and gives rise to clusters that reshape their environment through radiation and mechanical energy. Because dust often conceals the most active regions, multi-wavelength observations are necessary to build a coherent description. Radio lines trace cold atomic gas and measure large-scale streaming. Millimeter lines trace molecules that mark dense cold regions near gravitational instability. Infrared continuum maps warmer dust and the thermal irradiation from heated grains. Optical lines trace ionized gas around massive stars. X-ray observations detect hot tenuous plasma and the signatures of strong gravity near compact objects. Each band supplies a specific piece of the physical state of the medium. When combined, the data show a disk where structure and activity vary with radius, with vertical height, and with the presence of young clusters. This broad context defines the environment along the sightline through Cygnus. The field contains layered gas phases, a mix of stellar ages, organized magnetic structure, and flows driven by rotation and feedback. The bar and spiral arms guide gas into arcs and rings, and the warp and flare shape the vertical and radial distribution of a material. Observations across many wavelengths reveal how these elements together maintain a steady exchange among phases of the interstellar medium. Within such an environment, any emission or absorption seen along the direction of Cygnus must be interpreted against the complex but orderly behaviour of a barred spiral disk. The sky area called Cygnus presents a long crowded window onto the galactic plane, and within this frame the narrator traces a careful path that sets orientation, distance and context before any particular object is considered in detail. The constellation itself is anchored by bright stars that form a cross-like pattern, with the long arm aligned roughly along the plane of the Milky Way and the short arm rising above and below it. This field is dense because the line of sight runs close to the midplane where star counts rise and dust lanes gather along the same geometry. The glow that threads this region in dark nights is the integrated light of many distant stars seen through a screen of dust that dims and reddens as the distance increases. Interstellar dust grains are tiny solids that absorb and scatter blue light more than red light, so a population that is intrinsically mixed in colour appears shifted toward warmer hues as it is viewed through thicker columns of dust. The effect is not uniform because clouds are irregular and layered. It varies across the frame and with distance, so any careful reading must couple colour with position and with the signatures of gas seen at many wavelengths. Astronomers define a coordinate system tied to the galactic centre and to the plane so that longitude increases along the disk and latitude measures height above and below it. Cygnus sits near longitudes that cut through an inner section of the local spiral environment, and this sightline intersects multiple complexes of gas and young stars that overlap in projection, though they lie at different ranges. The challenge is to separate these layers, and the method is to combine measurements of distance, motion and composition until a coherent three-dimensional picture emerges. Parallax, the slight shift in position of a star as Earth orbits the Sun, provides direct distance for nearby bright sources, and when those anchors are in place, other distances can be tied by comparing standard candles, which are objects with well understood luminosities, and by using the velocities of gas traced in radio lines to estimate positions along the arm pattern. In Cygnus, the task is made harder by differential extinction where dust is patchy and strong in some narrow zones, and by emission that glows from ionized regions around massive stars that can mask faint populations behind them. The frame therefore needs many windows. In the radio-neutral, hydrogen marks the diffuse atomic component between denser clouds, and its Doppler-shifted line separates features by their motion along the line of sight. In the millimeter molecules, such as carbon monoxide, trace cold shielded regions where stars form, and their narrow lines lay out filaments and clumps that would be invisible in optical light. In the infrared, dust warmed by starlight re-radiates, and young stars that are still embedded in their natal envelopes become visible even when thick dust hides them in shorter wavelengths. In the optical, recombination lines from hydrogen and forbidden lines from oxygen outline ionized shells and bright fronts at the edges of cavities carved by radiation and winds. In X-rays, hot plasma from recent activity and from supernova heated gas draws a map of energy injection into the medium. The whole frame is a layered cross-section of a spiral disk in motion, and each band emphasizes one layer of physics, so only in combination does the window become legible. Within this window, starfields vary with latitude as the sightline lifts above and drops below the midplane. At small positive or negative latitudes, the foreground thins a little, and the number of overlapping structures is reduced, but the dominant effect remains the same, a rich field where distance must be established before luminosity or size can be understood. The bright star often used as a reference in this field is Deneb, a luminous supergiant that marks one vertex of a well-known asterism. And though it's not physically connected to many of the clouds seen along the plane, its placement in the frame helps observers fix orientation when they step between wide and narrow views. The polarization of starlight across Cygnus traces interstellar magnetic fields because elongated dust grains align with the field and preferentially absorb certain orientations of light, and these maps show ordered patterns on large scales that bend with the warp of the disk and twist near the edges of cavities blown by clusters. Magnetic fields influence how gas collapses by guiding charged particles and by adding pressure that can slow or channel flows, so their orientation is a key part of the context in which any compact source sits. The radiation field also varies across the frame hard near young clusters, where ultraviolet light is strong and softer in the spaces between, and the hardness of the field determines how deep ionization fronts penetrate into clouds and how molecules survive in the outer layers. The kinematics of gas reveal streaming along the spiral pattern, and motions driven by the gravitational potential of the bar, so line profiles often show multiple components that must be disentangled before a structure can be assigned to a particular arm or ring. The sightline through Cygnus intersects superbubbles created by the overlapping activity of many massive stars, and at their boundaries thin shells glow and sometimes fragment into pillars and globules,
by utilizing the
where
hue,
new stars
position,
may
and
form
spectrum
under the
data from
pressure
these
of the
maps of color and
expanding
motion,
fronts.
we uncover the
The
universe's
presence of
hidden
compact
architecture.
remnants, including neutron stars and black holes, is inferred in this field by variability and by high-energy emission from accretion, the process in which gas falls toward a deep potential well and heats as it loses orbital energy. X-ray
There, the
binaries in
foreground
particular
dust
are
layer is
identified
separating cleanly
when a
now.
bright star shows
And the
spectral
velocity
lines
data
in a
confirms the
periodic
shift
shift
in the
that
CO
reveals
emission.
an unseen massive companion.
Parallax
And
provides
when
the
rapid
first rung
flickering
of the
in
cosmic
X-rays
distance
indicates a
ladder.
small
But to
emitting
measure
region
the
near a
truly
compact
immeasurable,
object.
we
The window, therefore, is not only a backdrop of stars and clouds, it is a laboratory where strong gravity radiation and magnetism
Windows
couple to
across
matter in many
wavelengths.
regimes.
From
To
visible
maintain
light
a
to
steady
the
reading,
pulsing
the
energy
narrator
of
sets a
radio
scale
waves,
from the
the
broad
heat
Milky Way
signatures of
disk down
infrared.
to the subsection that
Follow
sits
the
in this
21
frame,
centimeter line
then to the
as it
specific
divides the
crossings of
sky
spiral
into
arms
layers
that
of
the line of
moving
sight
gas.
encounters, and then to the clusters and
molecules in the cold
associations
reveal
within
how
those
carbon
crossings.
monoxide marks the
The
birthplaces
first
of
step
new
is to
stars
accept that
within
brightness
hidden
on the
filaments.
sky is not a measure of proximity, because a luminous cluster behind modest dust can outshine a nearby group behind heavier extinction, and a faint distant association can be rendered almost invisible by a strong foreground cloud. The second step is to tie features across wavelengths so that a cavity seen in radio and a shell seen in optical emission lines describe the same structure, and then to use stellar distances and velocities to place that structure in 3 dimensions. The third step is to attend to time, because variable sources in this frame change brightness and spectrum on timescales from fractions of a second to many years, and those changes reveal size and depth that a static image cannot. In Cygnus, this careful assembly has produced maps where strands of molecular gas extend for hundreds of light years and connect clusters that sit at the same distance, where hot interiors of superbubbles vent into the halo through chimneys, and where young stars trace recent compressions along
These
fronts.
invisible magnetic
It has
threads
also
channel
revealed
the
a set of
diffuse gas,
compact X-ray
shaping its slow
sources
collapse.
with distinct behaviors,
hard
some
and soft.
softer and steadier, some
Contrast the
harder
harsh
and more
ultraviolet
variable,
of young
that sit
clusters
against
with
the
the gentler
crowded
glow
field and
between them.
require sustained attention to
of
separate and to
ionization.
understand. A lesser known point in this window is the presence of long, faint radio filaments that align with the large-scale magnetic field, and that may mark relics of past energy injection or slow-ordered flows shaped by the field geometry. They do not dominate the bright view, but they add a layer of structure that is only visible in sensitive maps. An uncertainty that remains is the exact 3-dimensional relation of some overlapping
Where shells
complexes
become
whose
seeds.
velocities are
The
similar.
expanding fronts of these supernova
because of
remnants
streaming
ignite
along
new
the arm.
rounds of star formation.
Without high precision distances for many members, models of their shapes and connections retain multiple allowed configurations. A planetary scale observation is that the view is a small section of a wider barred spiral disk in which stars' gas fields and radiation are coupled across large ranges of scale, and that the behaviours seen here are examples of processes that recur across the
Radiation
plane.
scrubbers
With the
performed
window now
optimally.
set, the narrator
Data
can move
acquisition is
inward from
complete.
this wide sky frame through the layered dust and gas towards specific structures where a compact unseen mass draws matter into a bright flow that signals strong gravity at work.
Brightness
Along the sight line
is
through
not
Cygnus, the
nearness.
narrator now enters the outer spiral environment where gas, dust and young stars mark the lanes that feed formation on large scales. The spiral segment encountered here is part of a pattern that moves as a wave through the disk, and although individual stars and clouds stream through the pattern, the overdensity persists and shapes how material collects. The arm is not a single ridge, but a braided set of filaments, shells and cavities with
Faint
thickness in both
filaments
height and
aligned
radius.
with magnetic
Within
fields.
it, cold molecular gas threads the
Echoes of
midplane in long strands, while warmer atomic gas wraps around these strands like a sheath, and still hotter ionized gas fills cavities where
Quiet
clusters have recently
geometry
injected
of a
energy.
spiral.
The mixture forms a layered scaffold that supports new clusters at the junctions of
density
filaments and at the rims of
becomes light.
expanding shells. The narrator follows these structures as they arc across the frame, noting that their apparent contiguity on the sky is often the projection of several segments at different distances that align along the line of sight. Even so, coherent velocities and matching chemical signatures identify stretches that truly belong to the same section of arm. In those stretches, gravity, turbulence and magnetic fields combine to assemble clouds with masses large enough to form luminous, short-lived stars. The consensus picture holds that spiral compression and converging flows help raise densities until cooling becomes efficient and self-gravity wins over support. Once dense clumps appear, they fragment further and cause collapse to produce stars. The most massive stars that result dominate the local energy budget, with radiation and
Starlight
winds
against
carving
the dark.
ionized bubbles and driving shock fronts into the surrounding medium. These fronts sweep up shells that can become unstable and form a new generation of stars along their edges, a process that chains activity along the arm.
And the field.
Because the line of sight in Cygnus runs close to the plane, it crosses several such chains that are at different depths, making the field unusually rich in overlapping edges, pillars and cavities. Star formation in this environment is not
Where
uniform
pressure
in time.
fails,
It advances
fields
in
prevail.
bursts where flows collide, or where an expanding shell meets a filament at a favourable angle, or where bar-driven streaming compresses gas against the arm's inner edge. The narrator attends to the role of shear, the slight difference in orbital speed with radius, which can stretch clouds and filaments while also supplying ordered motion that seeds instabilities. Magnetic fields oriented partly along the arm by large-scale rotation and partly twisted by local turbulence lend additional support and guide flows, yielding filaments that align over many tens of light years. Dust grains mixed into the gas shield the interiors of clouds from harsh radiation and allow molecules to survive. They also re-radiate absorbed starlight in the infrared, gently cooling dense regions and enabling collapse. The chemical state of the arm reflects many cycles of star birth and death.
From the ashes
Heavy
of
elements
stellar
forged in
death come the
earlier
seeds of
generations have
rebirth.
enriched the gas
These heavy
to levels typical of the inner portion of the outer disk, and those elements act as efficient coolants in dense regions, quickening the pace from
The
compression to
dispersal of
fragmentation.
clusters.
Yet
Watch how
abundance
open
measurements
clusters
vary
dissolve
across
and
the arm
scatter,
because mixing
leaving
is
faint
incomplete,
traces of their
and because
origin.
recent inflow from the halo can introduce gas with lower enrichment. A lesser-known feature of this sector is the presence of kilometre per second scale coherent velocity fibres inside molecular filaments, narrow strands that retain uniform motion over surprisingly long distances. These
This
fibres
is the
appear
dance
to
of
organise
angular
where cores
momentum.
form, suggesting that
As
flow
gas
geometry,
rotates.
not just gravity, helps set the initial conditions for clusters. The narrator notes that in some places long molecular filaments intersect at hubs where many young objects are clustered, while in others chains of small clumps run for hundreds of light years, with only modest star formation, implying that the lifetime and pressure history of the gas control how far the sequence has progressed. Embedded within the arm are associations of very massive stars whose light dominates their neighbourhoods. Their ultraviolet radiation creates extended ionized zones with sharp fronts where it meets denser material. Inside these zones, windswept cavities expand and collect bright rims that mark where pressure piles gas into compressed shells. Beyond the shells, neutral layers fold back into the cold filaments that thread the midplane.
Energy.
Supernovae from the earliest
Trace
massive
the journey
members
of
of an
starlight
association
as it becomes
punch through the
heat,
cavity walls,
turbulence,
venting
and
hot gas
shadow.
upward and forming chimneys that connect the disk to the lower halo. The energy that escapes does not vanish. It fills the surrounding volume with tenuous million-degree plasma that cools slowly and helps to balance weight against gravity in the system's thick layers. The narrator follows one such super bubble across the frame, aware that its visible rim may be only one segment of a much larger incomplete loop that the line of sight slices at an angle. Gas motions inside the arm reflect not only local feedback but also the broader gravitational field of the bar and the shape of the spiral potential. Streaming motions along the arm add or subtract a few tens of kilometers per hour to the orbital flow, shifting line profiles and complicating kinematic distance estimates. Where the arm curves toward the inner galaxy, crowding inversions and velocities of different layers blend. Where it sweeps outward, separation improves and layered structures are easier to assign to distinct distances. The warp of the disk slightly tilts the midplane, moving the densest layers north or south of the nominal latitude in different longitudes, and this geometric tilt changes where extinction is strongest and where star count's thin. Against this
By
structured
utilizing
background,
the
the
hue,
seeds of
position, and
compact
spectrum
remnants are
data from these
planted.
maps of color and
Massive
motion, we
binaries
uncover
born in
the
dense
universe's
clusters
hidden
evolve on
architecture.
short timescales. The more massive member swells loses mass in a wind and eventually collapses to a compact object. Whether it leaves a neutron star or a black hole depends
The
on mass
spiral
composition
beneath the cross.
and the details of the explosion or direct collapse.
There,
In
the
wind-rich
foreground dust layer
environments
is
like those
separating
hosted by
cleanly now.
supergiant companions, the
velocity
compact
data
object
confirms
can
the
accrete
shift in
from
the
the
CO
stellar
emission.
wind and emit X-rays that
Parallax
flicker on
provides the
short
first rung of the
timescales,
cosmic
betraying a
distance ladder.
small,
But to
deep
measure the truly
potential
immeasurable,
well.
we
The narrator emphasizes that the presence of such a system is consistent with a setting that is young in stellar terms, where the
Windows
initial
across
mass
wavelengths.
function has produced
From
several
visible light
very
to the
massive
pulsing
stars
energy
in
of
close
radio
pairs.
waves, the heat
A point of
signatures
uncertainty
infrared.
remains in the
Follow
exact
the
formation
21
channels for the
centimeter line
tightest
as it
massive
divides the
binaries
sky
that later
into
host
layers
black
of
holes.
moving gas.
It is not fully established how
Molecules in
common
the cold
envelope
reveal how carbon
phases,
monoxide
where
marks
one
the
star
birthplaces of
engulfs
new
its
stars within
companion
hidden
inside a
filaments.
shared gaseous envelope, proceed in detail in high-mass, high-luminosity systems, nor how often such phases end with a close pair that survives until collapse. Observations of the arm provide indirect constraints through the demographics of young clusters
This
and the
high-temperature
fraction
map
of
shows how
massive
X-rays
stars
chart the
observed in
immense
close
energy of stellar
pairs.
explosions,
But the
and
mapping from
powerful
those
pull of
numbers
gravity
to a
combined.
precise channel remains incomplete. This uncertainty does not weaken the broader frame. It marks the frontier where current models meet complex physics of mass loss rotation and envelope ejection. The arm also hosts runaway stars, high-velocity
Deneb,
objects ejected from
luminous
clusters by
anchor.
dynamical interactions or supernova kicks. Their paths cut across the orderly lanes and sometimes point back to dense hubs where interactions were common. These runaways carry with them bow shocks where their winds meet the surrounding medium faint arcs that align with their motion and sketch the shape of the local flow. Such signatures,
These
subtle and
invisible
crowded
magnetic
fields add to the
threads
set
channel
of
the
traces
diffuse
that
gas,
reveal momentum
shaping its
exchange and
slow
energy
collapse.
distribution in the
Radiation
arm.
hard
As the
and
narrator
soft.
tracks these details,
Contrast
the
the harsh
planetary scale
ultraviolet of
perspective
young
is kept
clusters
in view.
with the gentler glow
This spiral
between them.
environment is
The
one
depth
repeating
of
unit in a
ionization.
disc-wide pattern,
This
and its
is how
cycles of
radiation
gas
sculpts the
compression,
edges of
star birth,
molecular clouds.
feedback and mixing are mirrored in other arms and other longitudes. The behaviour seen here is not unique to Cygnus. It is a local instance of a general process that keeps the disk active over long intervals. Within this outer spiral setting, conditions are now in place for the emergence of a wind-fed X-ray binary. The layered medium
Where
supplies the raw
shells
material.
become seeds.
The clustered
expanding
formation
fronts
of
these
massive
supernova
stars
remnants
provides
ignite new
progenitors,
rounds of star
and the dynamics
formation.
of close pairs sets the stage for strong gravity to shape light. The narrator prepares to move inward from the scale of the arm and its associations toward the specific binary, where an unseen compact object orbits a luminous supergiant and where the flow of a stellar wind becomes the fuel for a persistent high-energy source that will be read in timing spectrum and motion against the busy
The
backdrop of
dampening
the arm.
field held stable
Within the
at
spiral
500
environment,
GRC.
the narrator
Radiation
narrows to
scrubbers
the
performed
birth and
optimally.
evolution of
Data
massive
acquisition is
stars and to
complete.
the close pairs that set the stage for compact remnants. Massive stars form where cold dense gas reaches high column densities along filaments and at their junctions.
Brightness
Gravity draws
is
matter
not
inward, while
nearness.
turbulence and magnetic fields slow the collapse enough to channel flow through disks and along preferred directions. As a young massive object gains mass radiation, pushes back on the inflow, but observations and models show that accretion does not cease. Material continues to stream through a thick disk and is vented by bipolar outflows that carry away angular momentum. These outflows carve
Faint
cavities in the
filaments
surrounding
aligned with
clouds so that
magnetic fields.
radiation escapes along the poles while
Echoes
gas
of-
still feeds the disk near the plane. The result is efficient growth to high mass within a short interval measured in a few 100,000 years. Clusters
Quiet
provide the typical
geometry
setting
of
because
a
the densities
spiral.
needed for massive star formation arise where many stars are forming at
Where
once and where
density
gravity from the whole
becomes
region
light.
deepens the well. In these clusters, close encounters and shared birth conditions favour the formation of multiple systems, so the multiplicity fraction for the heaviest stars is high. Many of these pairs begin their lives with separations that allow strong interaction later, and that interaction controls how mass and angular momentum move between the stars and into the surrounding space. The initial mass function describes the relative numbers of stars born at each mass. It declines toward higher mass, so massive stars are rare, but their influence is large because they radiate intensely, drive fast winds and end their lives quickly. They set the radiation field in their neighbourhoods and seed the medium with heavy elements when they die. A typical massive star spends only a few million years on the
Starlight
main
against
sequence,
the
burning
dark.
hydrogen in its core. After core hydrogen is exhausted, the core contracts and heats while the outer layers expand. The star may cross regions of the temperature
The
scale that
filament
lead to strong pulsations and
field.
changes in wind strength. Mass loss through winds becomes a central factor in the subsequent evolution, because it strips the envelope, reveals deeper layers, and changes the size and luminosity of the star. Metal content influences wind
Where
strength
pressure
through line-driven
fails,
acceleration.
Fields prevail.
At higher metal content, winds carry more mass and angular momentum into space. Rotation adds another layer by mixing material inside the star and by shaping winds at the surface. Magnetic fields, when present, can confine winds and create structured outflows that channel mass loss into streams and loops. In a binary, the radius of a star relative to a boundary called the Roche lobe determines whether gas is transferred by a stream. The Roche lobe is the region around a star inside which material remains bound to that star in the combined gravitational and rotational field of the pair. If a star expands enough to fill this lobe, gas flows through the inner point between the stars and is accreted by the companion or forms a disk around it. Mass transfer can be stable with a steady stream, or unstable with the runaway that engulfs the pair in a shared envelope. A shared envelope is a phase in which both stellar cores orbit inside a single extended gaseous envelope, while friction removes orbital energy and shrinks the separation. If the envelope is ejected before the cores merge, a tight binary remains, if not the pair coalesces. The physics of envelope ejection involves energy from orbital decay, recombination of ionized gas and interaction with dust and magnetic fields, and remains an area where models and observations are still being reconciled. When the more massive member of a close pair evolves first, it can transfer mass to the less massive companion, reversing the mass ratio. This reversal leaves a strip primary with a smaller envelope and a spun-up companion that may later evolve differently than a single star of the same mass. The stripped star can become a compact helium star, and if conditions allow, it may explode as a core collapse supernova or collapse directly to a black hole with little explosive ejection. Whether a supernova occurs or whether the collapse is quiet depends on the core structure, neutrino transport rotation and magnetic fields at the moment of failure of pressure support. Current studies highlight the sensitivity of the outcome to small differences in the late burning stages. If a supernova does occur, the remnant receives a kick from asymmetries in the explosion. Kicks can tilt or disrupt the orbit. Systems that remain bound after a kick carry memory of the event in their motion through the galaxy and in the eccentricity of the orbit. Systems that collapse more quietly without a strong explosion are expected to receive smaller changes in velocity, leaving the pair closer to the motion of its birth environment. The compact object left behind can be a neutron star or a black hole. The dividing line depends on the mass of the core and on details of the collapse. In a close pair with a luminous companion, the compact object can accrete gas either through a wind or through Roche lobe overflow. Wind accretion occurs when the donor star drives a fast outflow, and the compact object captures a fraction of that flow. Roche lobe overflow occurs when the donor star fills its lobe and gas streams directly through the inner point, often forming a disk around the compact object. A disk forms because the incoming gas carries angular momentum. Viscous processes in the disk convert orbital energy to heat and move mass inward, while angular momentum is transported outward. The inner parts of the disk become very hot and emit high energy radiation. A hot tenuous corona above the disk can scatter soft photons to higher energies, producing a hard X-ray component. In some states, magnetic fields tap rotational energy from the inner flow and launch collimated outflows called jets that carry momentum and energy away along the rotation axis. The observational signatures of a massive binary depend on the mass transfer mode and on the compact object type. Wind-fed systems show variability linked to changes in wind speed and density. Disks formed by Roche lobe overflow can show stable high states or transitions between soft and hard states, where the balance between disk and corona shifts. Timing studies measure rapid variability that constrains the size of the emitting region to scales near the compact object. Spectral features from iron near the energy of fluorescent emission can appear broadened and skewed by motion and by the strong gravity close to the compact object. These features allow measurement of the geometry of the inner flow, and in some cases constraints on spin through the location of the innermost stable orbit. Massive binaries are common in young clusters, but only a fraction will evolve into systems with compact remnants that remain bound and interacting. The path depends on an initial separation, mass ratio rotation, and the sequence of mass transfer episodes. Some pairs will widen and become detached, others will undergo a shared envelope phase, and emerge as close compact binaries, and a subset will form X-ray binaries where the compact object accretes from a still luminous torn donor. The demographics of
This
these
high
outcomes
temperature
are
map
measured by
shows how
surveys
X-rays
across
chart
the
the immense
galaxy
energy of
and by
stellar
population
explosion and the
synthesis
powerful pull
models
of
that
gravity
involve large
combined.
samples under different physical assumptions. A lesser-known detail is that many very young massive stars already show radial velocity variations, indicative of tight orbits with periods of only a few days to a few weeks. Such short periods imply that substantial
Deneb,
interaction is inevitable
the
early in
luminous
life,
anchor.
and that angular momentum lost through tides and winds can further shrink orbits before the first collapse. An uncertainty remains in the exact distribution of kicks imparted to newly formed black holes, and in how that distribution depends on the amount of mass ejected and fallback during collapse. Without precise knowledge of kicks,
These invisible
predictions of how
magnetic
many
threads
systems
channel the
survive the
diffuse
first
gas,
collapse and remain
shaping
bound
its slow
carry
collapse.
broad ranges.
Radiation hard and soft.
Another uncertainty
Contrast
lies in
the
wind
harsh
clumping the
ultraviolet of
small-scale
young
structure in
clusters with the
stellar
gentler
winds that
glow
changes
between
the
them.
effective mass
The
loss
depth
rates
of
and the accretion
ionization.
flow onto the compact object. This clumping alters both evolution and observable variability. From a larger perspective, the processes described here link local star formation to the state of the galaxy as a whole. The fraction of massive stars in close binaries, the metal content that sets wind strength, and the ambient pressure that shapes cloud collapse all vary with position in the disk and with time. Thus, the supply of future compact
Where
remnants
shells
and of
become
X-ray
seeds,
binaries depends on
The
galactic
expanding
scale
fronts of these
gradients and
supernova
on the
remnants
history of
ignite
inflow and
new
mixing.
rounds of star formation.
The narrator keeps the path strictly inward, from clustered birth to binary interaction to core collapse and compact object formation, and from the general mechanisms that govern these stages to the subset of conditions that yield a tight wind-fed pair with a deep gravitational well. Within that subset, the next region is the concrete configuration of a
dampening field
luminous
held stable at
supergiant
500
and an
GRC.
unseen companion
Radiation
in
scrubbers
close
performed
orbit,
optimally.
where the flow
Data
of a
acquisition
stellar
is
wind
complete.
is focused by gravity and processed through an accretion structure that shines in high-energy light. The narrator now fixes attention on a specific pair in Cygnus,
Brightness
where a luminous
is not
supergiant and an
nearness.
unseen compact companion move in a tight orbit and produce a steady source of high-energy light. The system sits at a distance of roughly 7,000 light-years, far enough that dust along the plane of the galaxy dims the optical view, but close enough for precise measurements across many wavelengths. The visible member is an early-type supergiant with a surface that is extremely hot around 30,000 Kelvin and a radius that
Faint
spans
filaments
many tens of
aligned with
times the
magnetic
radius of the Sun.
fields.
Its spectrum
Echoes
shows
of
strong lines shaped by a powerful outflow, a stellar wind that streams away from the surface at speeds of thousands of kilometers per second.
The quiet
The star's light
geometry
and wind
of a
define
spiral.
much of what is seen at long wavelengths, while the compact companion announces
Where
itself in
density
X-rays through the
becomes light.
heat and motion of gas as it falls deep into a gravitational well. The orbit is short. The pair completes a revolution in a little less than 6 days, which places the separation at only a few times the radius of the supergiant, and means that tidal forces are important in shaping the star and its wind. Radial velocity measurements of the star's absorption lines trace a clean sinusoidal shift through the orbit and provide a firm handle on the mass function, the basic constraint that combines period and amplitude to bound the masses. With additional information about inclination and the properties of the donor, those bounds sharpen into estimates that place the unseen object well above the maximum mass expected for a neutron star. The compact companion is therefore interpreted as a black hole with a mass of roughly 20 to 25 times the mass of the Sun, while the supergiant
Starlight
weighs in
against
at
the
several
dark.
tens of solar masses. Interferometric and radioastrometric work fix the distance and the proper motion by measuring tiny shifts in position over time. These measurements also reveal a
The
faint
filament
compact radio source
and the
that sits
field.
near the X-ray position and varies with the high energy state, a signature consistent with a weak jet or outflow from the inner accretion flow. The geometry of the system is constrained by several effects. The orbit is inclined at a modest
Where
angle to
pressure
the line of
fails,
sight not edge on,
fields
because no full
prevail.
eclipses are seen in the X-rays. Yet absorption changes between orbital phases show that the line of sight sometimes passes through denser parts of the wind. The supergiant does not fill its Roche lobe completely, so the mass transfer mode is wind capture rather than a direct stream through the inner point between the stars. Even so, tidal forces and radiation pressure focus the wind, producing a denser wake downwind of the black hole and a phase-dependent pattern of absorption and scattering that can be mapped by following the X-ray spectrum around the orbit. The basic fuel supply is set by the mass loss rate of the donor and the fraction of wind intercepted within the gravitational focus of the compact object. That fraction varies with wind speed clumping and the orbital motion of the pair. Gas that is captured circularizes under its angular momentum and forms a small accretion disk.
From the ashes of
In the
stellar
outer
death
parts of
come
the disk, the
seeds
gas
of
is
rebirth.
cooler and optically
These
thick,
heavy
while toward the center it becomes very hot. Above the inner disk lies a tenuous hot corona that scatters soft photons
The
to higher
dispersal of
energies and
clusters.
produces a
Watch how
hard
open
tail in the
clusters
spectrum.
dissolve and scatter,
Reflection
leaving faint
features
traces of
arise
their
when
origin.
the hard radiation hits the disk surface and is reprocessed, and these features include a broadened iron line that is distorted by relativistic motion and by the curved spacetime close to the compact object. By modelling the breadth and skew of that line, and by fitting the thermal continuum of the inner
This is
disk
the
during
dance
softer
of
phases,
angular momentum.
observers infer that the inner
As
edge of the
gas
flow
rotates.
lies very close to the last stable circular orbit, and that the black hole spins very rapidly near the theoretical upper limit allowed for a rotating black hole. Timing properties add to this picture. The X-ray light fluctuates rapidly with power spread over many timescales and with characteristic peaks that shift with state. Such rapid changes point to a small emitting region measured in tens of gravitational radii because larger regions cannot vary coherently on such short intervals. When the source hardens, the corona dominates and the radio source brightens, consistent with a state where magnetic fields in the inner flow collimate a weak steady outflow. When the source softens, the thermal disk brightens and the radio weakens, consistent with a state where the jet is suppressed and the inner flow cools. These state changes in this system are more modest than in
Trace the
some
journey of
transient
starlight
systems
as
because
it
the
becomes
fuel
heat,
supply from the wind is
turbulence,
steady and
and
the disk
shadow.
is small, but they follow the same broad pattern seen in many accreting black holes. The wind of the supergiant is structured rather than smooth. Clumps with higher density move through the flow and change the accretion rate on short timescales as they pass the compact object. These inhomogeneities produce dips and bursts in the X-ray light curve and can be studied by measuring how the soft part of the spectrum is absorbed as a function of time and orbital phase. The ultraviolet radiation from the inner flow can also ionize parts of the wind and change its acceleration, feeding back on the mass capture rate. The combination of wind clumping and ionization feedback helps explain the complex but repeatable variability patterns seen across many orbits. The stellar photosphere and the inner disk leave imprints on the spectrum that allow the narrator to assemble a coherent set of parameters. The donor is classified as a late O-type or very early B-type supergiant with a temperature of tens of thousands of Kelvin a luminosity, hundreds of thousands of times that of the Sun, and a wind mass loss rate that can be expressed in a fraction of a solar mass over a
scattering
million
the blue
years.
starlight and allowing
The
warmer
orbit has a
tones to
small but
dominate.
measurable
causing
eccentricity, indicating that past mass transfer and possible natal motion did not perfectly circularize the pair, although tides
By
continue to
utilizing the
work to
hue,
reduce the
position, and spectrum
eccentricity.
data from these
The
maps
black
of color
hole
and
mass,
motion,
the distance,
we
the
uncover the
inclination
universe's
and the
hidden
spin together,
architecture.
define a reference system used to test models of accretion and to benchmark techniques for reading gravity from light. A lesser known detail is that the preferred distance and inclination used today come not only from optical parallax to the bright star,
There, the
but
foreground
also
dust
from
layer
radio
is separating
parallax
cleanly
to
now.
the compact source,
And the
when
velocity
it is
data
bright enough
confirms
to
the
image,
shift
so
in
the
the CO
same
emission.
geometry is tied across the full
Parallax
range of
provides the
wavelengths.
first rung on the cosmic
Another
distance
detail
ladder.
is that the star's
But to
shape is
measure
not
the truly
perfectly
immeasurable,
spherical,
we
because tides raise a slight bulge toward the companion, This distortion can be detected as a repeated brightening and dimming
Windows
over the
across
orbit
wavelengths,
called
from
ellipsoidal
visible
modulation,
light to the pulsing
which helps to
energy of
fix the
radio waves,
inclination
the heat
and the
signatures
size of the
infrared.
star relative to the
Follow
orbit.
the 21
An
centimeter
uncertainty
line
that
as it
remains
divides
concerns
the
the
sky
exact
into layers
mapping
of moving
between
gas.
wind structure at the scale of the
Molecules in the
donor's
cold reveal
atmosphere
how carbon
and the
monoxide
small-scale
marks the
flow that
birthplaces of
crosses
new
into the
stars
black
within
hole
hidden
sphere of
filaments.
influence. Measurements show that the wind is clumpy, but the size, density, contrast and distribution of clumps remain topics of active study, and those properties strongly affect the accretion rate and the appearance of the X-ray spectrum.
This
Another open
high-temperature map
question is
shows
the
how
precise
X-rays
value
chart
of
the
the black
immense
hole
energy of
spin and
stellar
how that spin was
explosions
built.
and the powerful pull of
Current
gravity
techniques
combined.
favour a very fast spin, but whether that is mostly natal inherited, at formation, or the product of a long history of accretion is not fully settled, because wind-fed accretion may not deliver enough angular momentum over the lifetime of the system
Deneb,
to alter the spin
The
substantially.
luminous anchor.
A planetary scale observation is that the binary, although only one system in one arm, provides a laboratory that links stellar astrophysics, strong gravity plasma physics, and the ecology of the galactic disk. The way its wind interacts with radiation and magnetic fields echoes processes that occur in other
These
massive
invisible
binaries
magnetic
across the
threads
Milky
channel
Way.
the diffuse
The
gas,
X-rays it
shaping
emits
its
contribute to
slow
the
collapse.
high-energy background
Radiation
that
hard
warms
and
and
soft.
ionizes diffuse gas
Contrast the
far
harsh
from
ultraviolet
star-forming
of young
regions.
clusters
The
with
metals
gentler
forged
glow
in
between
earlier
them.
generations and
depth
present
of
in the star's
ionization.
atmosphere show how galactic
This
chemical
is how
evolution
radiation
sets
sculpts the
boundary
edges of
conditions for
molecular
present-day
clouds.
winds and mass loss. The motion of the pair through the disk records its origin in a young cluster and the dynamical history since the first collapse. By assembling its distance, masses, orbit, inclination, wind properties, and high-energy behaviour, the narrator completes the step from the outer spiral pattern to a single concrete system where measurements fix parameters closely
Where
enough to read
shells
strong
become
gravity at
seas.
work.
The expanding
The path
fronts of
remains
these
strictly
supernova remnants
inward.
ignite
The
new
next
rounds
region
of
is the
star
focused
formation.
flow of the stellar wind as it approaches the compact object where gravity shapes awake shocks form and gas crosses the boundary from the stellar environment into the immediate domain of the accretor. The narrator moves inward to the region where the supergiant's outflow encounters the black hole's gravity, and the fast line-driven wind becomes a focused gun stream. The donor sheds mass through a radiation-driven wind, propelled by absorption in
Radiation
metal
scrubbers
lines in its
performed
hot
optimally.
atmosphere.
Data
Near
acquisition
the
is
stellar
complete.
surface, the wind accelerates from subsonic to supersonic speeds and reaches several thousand kilometers per hour within a short radial distance. Left undisturbed,
Brightness
such a wind would
is
expand
not
roughly
nearness.
radially, with density falling as the inverse square of distance. In a binary, the black hole's gravity diverts part of this flow. Gas passing within a characteristic radius set by the ratio of gravitational pull to the square of the relative velocity is deflected, shocked, and captured. This gravitational focusing creates an accretion wake that bends behind the compact object and trails through the orbit like a dense ribbon embedded in a more diffuse
Faint
stream.
filaments
Because the
aligned
star
with
does
magnetic
not
fields.
fill its Roche lobe, there is no
Echoes of
direct
old-
stream through the inner point between the pair. The flow is controlled instead by the geometry and speed of the wind and by the orbital motion that
quiet
twists the
geometry
pattern in the
of a
corrotating
spiral.
frame. The path of gas from the stellar surface to the vicinity of the compact
Where
object is
density
not smooth.
becomes light.
The wind is intrinsically clumpy, shaped by instabilities in line driving that produce over dense parcels separated by regions of lower density and different ionization. Clumps alter the local mass flux by orders of magnitude on short timescales, so the rate at which the black hole captures material flickers as clumps pass through the focusing volume. The compact object also floods its surroundings with X-rays that ionize the wind and change its acceleration. Ionization reduces line opacity in the affected region and weakens radiative driving, creating a shadow of slower moving gas on the side of the star that faces the black hole. This slower gas is more easily captured, The result is a feedback loop in which accretion regulates wind speed and wind speed governs accretion efficiency. The orbit introduces periodicity. As the compact object moves around the star, the line of sight to Earth crosses different parts of the flow. At phases when the path passes through the wake and the denser inner wind, the soft X-ray spectrum is more heavily absorbed. At phases when the path avoids the wake, the spectrum is cleaner. Monitoring across many orbits maps the density and ionization structure and reveals that the wake trails the compact object by an angle that depends on wind speed and orbital velocity. The wake also supports shocks where streams converge, and these shocks heat gas to X-ray, emitting temperatures and imprint narrow absorption lines from highly ionized species onto the spectrum. The narrator reads these lines as the traces of the velocity field in the wind and as indicators of the changing ionization state through the orbit. As captured gas loses energy in the wake, it circularizes into a compact disk around the black hole. The disk is small compared with those in systems fed by Roche lobe overflow, but it is sufficient to process the flow and to organize angular momentum transport. The boundary between ballistic trajectories in the wake and orbital motion in the disk is a region of strong shear and turbulence where shocks and magnetic stresses heat the gas. In standard pictures, viscosity in the disk arises from magnetorotational turbulence. In a wind-fed system, there may be an additional source of turbulence where colliding streams from different parts of the wake intersect. The outer edge of the disk receives erratic feeding from clumps, so the inner emission responds with a mixture of steady and flickering components. A consensus point in this region is that the mass supply is dominated by gravitational focusing of the donor's wind rather than by a Roche lobe overflow stream. Orbital geometry, lack of full eclipses, and the absence of a persistent bright optical disk support this. A lesser-known detail is that the focused wind can create a quasi-stationary stagnation point ahead of the compact object in the corrotating frame where ram pressure of the incoming stream balances pressure in the wake. The location of this stagnation point moves with the ionization state of the wind, and its drift may contribute to slow quasi-periodic modulation in absorption that is not strictly locked to orbital phase. The inner wind is sculpted by radiation forces and by the star's rotation. If the equator is darker and the poles brighter, a pattern called gravity darkening, wind strength can vary with latitude, and the orbiting companion then samples a wind whose properties change as it passes under different stellar latitudes. The donor's weak magnetic field, if present, can confine a fraction of the wind near the surface and feed structured streams that are released intermittently, adding to clumpiness. These processes are subtle and difficult to measure directly, but the accumulated X-ray and ultraviolet data suggest that variability in the captured flow owes as much to the launch physics of the star as to hydrodynamics near the black hole. The geometry of the accretion wake has further observational consequences. As the compact object moves behind the star from the observer's viewpoint, photons from the inner flow scatter through the wind and produce a halo of delayed light that softens the observed spectrum. At other phases, resonance scattering in the wake adds narrow absorption features that deepen and shift with orbital motion. In very soft states, when the inner disk brightens, the enhanced X-ray luminosity pushes the ionization front outward, reduces line driving over a larger solid angle, and increases the fraction of slow wind available for capture. In harder states, when the corona dominates, the spectrum changes, but the total ionizing power can remain high, so the balance between acceleration and capture still favors focusing. These state-linked changes appear as small shifts in the phase of maximum absorption and in the amplitude of orbital modulation in the light curve. The dynamics within the wake and the outer disk
The
set
dust
the
acts as a
boundary
filter,
conditions for the
scattering the blue
innermost
starlight and
flow.
allowing the warmer tones to
Gas
dominate.
that enters the disk
causing the
with higher angular momentum settles at a larger radius, lengthening the time it takes to reach the region where most of the high-energy radiation is produced.
By utilizing the hue,
Gas that
position,
arrives
and
with
spectrum
lower
data
angular
from these maps
momentum
of color
plunges
and
deeper
motion,
before
we uncover the
circularizing and can
universe's
drive
hidden
brief,
architecture.
intense flares as it dissipates energy in strong shocks. The hot corona that overlies the inner disk is fed by evaporation from the top layers of the disk and by magnetic
The
reconnection
spiral
that heats
beneath the
tenuous
cross.
gas. In a wind-fed system, the coronal density
There,
may
the
be
foreground
influenced
dust
by the
layer is
composition and
separating cleanly
ionization of the incoming stream,
And the velocity data
because
confirms
heavier
the
elements
shift in the
carry
CO
more
emission.
electrons per unit mass and
Parallax provides
change
the
cooling
first rung
rates.
on the cosmic
The
distance
narrator
ladder.
notes that the
But to measure the
helium-enriched
truly
wind
immeasurable,
expected from an
we rely-
evolved hot supergiant yields a slightly different cooling curve than a solar composition plasma, and that this difference
Windows
can affect
across
the ratio of
wavelengths,
soft to
From
hard
visible
emission
light to
in
the
the inner
pulsing
flow.
energy of radio waves.
An
the heat
unresolved
signatures of
mystery in this
infrared.
region is the precise
Follow the
mechanism that
21
sets the
centimeter
geometry
line
and
as it
persistence of the hot
divides the
corona
sky into
in the
layers
presence
of
of a
moving
small
gas.
stochastically fed disk.
Molecules
In many
the core
transients with
reveal how
large
carbon
disks,
monoxide
transitions
marks the
between hard and
birthplaces of
soft
new
states are
stars within
linked to
hidden
global
filaments.
changes in accretion rate and disk structure. In this wind-fed system, the accretion rate varies on short timescales but remains moderate on average. Yet a stable corona survives for long intervals. Whether this stability is maintained by continuous
high-temperature
magnetic
map
heating
shows
driven
how
by the
X-rays
shear at
chart
the
the
disk
immense
edge,
energy of
by
stellar
evaporation,
explosions and the powerful
controlled
pull
by
of
the
gravity
compactness
combined.
of the disk, or by coupling to the jet that carries away energy remains under study. Another uncertainty lies in the three-dimensional shape of the accretion wake. Simulations show a range of patterns depending on wind speed, clumpiness, and ionizing
Denim.
flux, from smooth
luminous
curved
anchor.
sheets to fragmented knotty trails. Matching these patterns to observations requires higher cadence phase-resolved spectroscopy and tomographic reconstruction that is only now becoming practical. On planetary scales, the focused capture of the stellar wind in this binary feeds the high-energy budget of the surrounding
These
sector
invisible
of the disk.
magnetic threads
The
channel
hard
the diffuse
photons
gas,
penetrate well
shaping
beyond
its
the
slow
immediate
collapse.
neighborhood and
Radiation hard
maintain a
and soft.
population of ionized
Contrast the
species
harsh
in diffuse
ultraviolet of young
gas,
clusters with the
adding
gentler
to the
glow
thermal
between
and
them.
ionization balance
depth
of the
of
interstellar
ionization.
medium. The momentum
is how
carried by the
radiation
wind and by
sculpts
any
the
weak
edges of
jet
molecular
contributes to
clouds.
stirring gas nearby and to seeding pressure in the lower halo. The metals carried by the wind and eventually shed by the donor enter the shared reservoir that later forms new generations of stars, so the mass exchange that fuels accretion is simultaneously part of the galaxy's long-term chemical evolution. By tracking how the wind is
Where
focused,
shells
slowed
become
and
seeds.
captured,
The
the narrator
expanding fronts of
seals the
these
connection
supernova
between
remnants
stellar
ignite new
atmospheres and
rounds of
strong
star
gravity,
formation.
and fixes the inner boundary conditions that will govern the structure and light of the disk and corona. With the capture geometry in place, the path presses inward to the circularization region and to the formation of the compact, optically thick disk, where turbulence, viscosity, and radiation carry matter from the outer edge of the flow toward the innermost stable orbits around the black hole. From the
dampening
focused
field
wind
held
and its
stable at
wake, the
500
narrator
GRC.
follows the captured
Radiation
gas as it
scrubbers
sheds
performed
disorder
optimally.
and assembles into
acquisition
a
is
compact
complete.
rotating disk. The key transition is circularization, the process by which a stream with mixed directions becomes an orderly set of near
Brightness
circular orbits
is
around
not
the black
nearness.
hole. Gas approaches with specific angular momentum set by where it entered the capture region and by the geometry of the wake. Collisions within the stream and shocks where strands intersect convert directed kinetic energy into heat. That heat radiates away pressure drops and the paths tighten until an orbiting structure emerges. The outer rim of this new disk is not a sharp
Faint
wall,
filaments
but a region
aligned
of
with
stream
magnetic
impact and
fields.
shearing layers where parcels rain down
Echoes
at
of
different azimuths. Each impact stirs turbulence and seeds magnetic fields with fresh shear. The result is a rim that flickers as clumps arrive, and a body of gas within that slowly forgets the irregularities of supply and settles into differential rotation
density
where inner rings
becomes
revolve
light.
faster than outer rings under gravity. Angular momentum must move outward for mass to move inward. The agent that moves it is called viscosity. In a broad sense, any stress that transports angular momentum between neighbouring rings. In ionized disks, the leading candidate is magnetorotational turbulence, a process in which weak magnetic fields in a differentially rotating flow become tangled, stretch and tap orbital energy to drive correlated motions that behave like an effective viscosity. This turbulence produces a steady exchange in a gas, loses angular momentum, and sinks outer gas gains angular momentum and drifts outward. The energy extracted from orbits heats the gas, which then radiates. In the outer disk, the heat is carried away in optical and ultraviolet light. Deeper in where orbits run faster and dissipation is stronger, the radiation hardens and peaks at soft X-ray and extreme ultraviolet energies. The vertical structure of the disk resembles a layered atmosphere. Gravity presses downward, thermal pressure pushes upward, and in between radiation tries to escape. Near the midplane, the gas is dense and cooler, while the surface layers are thinner and warmer, bathed in
Where
light
pressure
from within
fails,
and from the compact
fields
corona above.
prevail.
Small grains and ions couple radiation and matter, so the opacity, a measure of how easily light passes, changes with temperature and with composition. At certain temperatures, hydrogen changes from neutral to ionized, altering opacity sharply. This transition imprints a thermal instability in some disks. A small rise in temperature can raise opacity, trap heat, and cause further heating. In large, slowly fed disks, this runaway creates cycles of bright and faint states. In this wind-fed system, the disk is small and supplied steadily, so the same physics is present but expressed as mild undulations rather than dramatic outbursts. The consensus point in this region is that differential rotation and magnetically driven turbulence carry angular momentum outward and allow gas to accrete. Observations of broad spectral energy distributions, rapid variability, and in other systems resolved velocity fields support this picture across a wide range of masses. Gas orbits do not lie in a perfectly flat sheet. Pressure magnetic stresses and the impact geometry make the outer disk slightly thick with a vertical scale height that grows with temperature. The disk can warp if radiation from the inner regions exerts uneven pressure on tilted surfaces, or if the black hole's spin axis is not aligned with the orbit. In that case, a general relativistic effect called frame dragging gently twists the inner flow so that its orbital plane precesses around the spin axis. If any such warping occurs here, it is subtle, because the orbit does not show deep eclipses, and the spectrum remains smooth through many orbital cycles. Still low amplitude, quasi-periodic changes in the X-ray light hint that the inner flow may nod and precess, slowly modulating how the corona sees the disk and how the jet base, if present, is oriented. The outer disk is fed erratically by wind clumps and maintains a narrow ring of enhanced density near the circularization radius. From that ring, matter diffuses inward under turbulent stresses. As it moves inward, the orbital speed increases, the power released per unit mass rises, and the temperature climbs. Radiation pressure, the push of light on matter, becomes important at these smaller radii and can swell the inner layers, making the flow more susceptible to vertical oscillations.
Energy in translation.
Above the disk, a tenuous, very hot layer. The corona intercepts some of the soft photons rising from below and scatters them to higher energies. The fraction of power that goes into this coronal channel changes with accretion conditions. When the fraction is high, the spectrum hardens and a faint compact radio source brightens, consistent with a link between coronal heating and the base of a jet. When the fraction is low, the thermal disk dominates the light and the radio weakens as if the outflow is quenched. A lesser-known detail concerns the composition of the wind-fed disk. The donor's outflow is modestly enriched in helium and in products of surface mixing. This composition shifts the cooling efficiency of the gas in the outer disk and slightly alters the temperature at which hydrogen ionizes through the vertical layers. Such changes can move the location where the thermal instability is strongest and can influence the detailed shape of the spectrum at soft energies without changing the overall behaviour. Another subtlety is the presence of a boundary layer between the ballistic wake and the outer rim, where Kelvin-Helmholtz shear instability is the same fluid instability that ruffles the edges of clouds on Earth,
The dust
roll up
acts as a
into
filter,
mixed streams.
scattering the blue starlight
These
and
rolls
allowing
can
the warmer
seed
tones
large
to dominate.
eddies that carry
causing
coherent
the dis-
structures inward, a memory of the feeding geometry imprinted on the disk that may be detectable as preferred timescales in the optical and
By
ultraviolet
utilizing the
flicker.
hue, position,
Radiation
and
from the
spectrum
inner
data from
disk
these
shines
maps of
upon the
color and
outer
motion,
disk and upon
we
any
uncover the
material lifted
universe's
above it,
hidden
a process
architecture.
called irradiation. Irradiation heats the surface layers and can keep the outer disk in a warm, partially ionized state even when the local dissipation is low.
The spiral
In wind-fed
beneath the
systems, this
cross.
effect can be strong because the inner flow is always hot.
There, the
By smoothing
foreground dust
temperature,
layer is
contrast
separating
irradiation
cleanly now.
may suppress large
And the
amplitude
velocity
outbursts
data
and help the
confirms the
disk
shift in the CO
maintain a
emission.
quasi-steady configuration.
Parallax provides
It
the
also
first rung on
enhances the
cosmic
visibility
distance
of
ladder.
broad emission
But
lines
to
formed
measure
in
the
the upper
truly
layers,
immeasurable,
lines that
we
respond to continuum changes with a small delay set by light travel time. Measuring that delay, a method called reverberation reveals the
across
scale of the
wavelengths,
emitting region
from visible
and tests
light
how
to the
far inward
pulsing
the
energy
optically
of
thick
radio
disk
waves,
extends
the heat
during different
signatures of
spectral
infrared.
states.
Follow
At still
the
smaller
21
radii,
centimeter
the
line
inner edge
as
of the
it
disk
divides
meets
the
the domain
sky
where
into
general
layers of
relativity
moving
sets the
gas.
permitted orbits. The
Molecules
innermost
in
stable
the coal
circular
reveal
orbit
how
is the
carbon
last ring where
monoxide
matter
marks the
can
birthplaces
circle
of
without
new
plunging
stars
inward.
within hidden filaments.
Its radius depends on the black hole's spin. When spin is high and aligned with the disk, the permitted orbit lies close to the event horizon. Spectra that show a very hot thermal peak and a strongly broadened ion line imply that the optically thick
This
flow
high-temperature
reaches
map
this inner
shows how
limit.
X-rays chart the immense energy of
Reflection
stellar
spectra add
explosions and the
support.
powerful pull of
A high
gravity
fraction
combined.
of coronal light appears to strike the disk surface and return with a smooth, skewed imprint that can only be produced if the disk extends deep into the potential well. The reflector acts like a curved mirror in strong gravity, blurring features and shifting them to lower energies. The unresolved mystery in this
The
region is the
luminous
persistent
anchor.
geometry of the corona and its coupling to the compact jet in a disk this small. Does the corona form a patchy layer above the inner rings, a compact lamppost near the axis, or a magnetically inflated inner flow that replaces the thin disk within a few gravitational radii? Each picture predicts a different
These invisible
pattern
magnetic
of
threads
reverberation
channel the
lags and
diffuse
a different
gas,
relation
shaping
between
its slow
X-ray
collapse.
hardness and radio flux.
Radiation hard and soft.
Current observations favour a
Contrast the
compact,
harsh
centrally
ultraviolet of young
concentrated source
clusters
during
with the
harder
gentler
intervals
glow between them.
and a more extended
The depth
laminar
of
structure during
ionization.
softer intervals.
This
But
is
the
how
underlying
radiation
heating
sculpts
process,
the
whether
edges of
dominated by
molecular clouds.
magnetic reconnection in tangled loops or by vertical dissipation in a mildly puffed inner flow, remains under debate. The scale and stability of the jet base are equally uncertain. In a system with steady but modest accretion, the outflow is weak and hard to map, yet its tight correlation with hard X-ray power hints at deep coupling between magnetic fields in the coronal
Where shells
volume
become
and the
seeds.
mechanism that lifts
The
plasma
expanding
out of the
fronts of these
potential
supernova
well.
remnants
The
ignite
disk
new
radiates
rounds of
not only
star
upward,
formation.
but also outward into the surrounding medium. Soft and hard photons leaving the inner few hundred gravitational radii stream through the wind and the wake, heating and ionizing gas far from the plane. This radiation maintains a halo of warm, partially ionized material around the system and imprints narrow blue-shifted absorption
The
lines
dampening
from
field held
ions
stable
such
at
as
500 GRC.
oxygen, neon
Radiation
and iron
scrubbers
in high
performed
states.
optimally. Data
Those
acquisition
lines
is
change
complete.
with orbital phase as the sightline traverses different chords through the wind. Over many cycles, the pattern reveals a three-dimensional density and ionization
Brightness
map of the
is
gas,
not
a tomographic
nearness.
view that connects the global structure of the disk to the larger scale environment of the binary. On planetary scales, the accretion disk in this one system contributes to the energy ecology of the galactic plane by adding hard photons that help keep diffuse gas ionized, and by stirring nearby clouds through radiation pressure and weak outflows. The heat and momentum it returns to its surroundings are small compared with the combined output
Faint
of the region's
filaments
massive
aligned with
stars,
magnetic
yet
fields.
spectral hardness and rapid variability
Echoes of
supply a distinct high-energy thread in the fabric of the interstellar medium. The same physics that governs this compact disk, the exchange of angular
quiet
momentum under
geometry
magnetic
of a
turbulence,
spiral.
and the balance between heating and cooling under changing opacity, recurs in disks around
density
young stars and in the
becomes light.
brighter disks of active galactic nuclei. Across these scales, the differences are of size and speed, but the equations that dictate flow and light share common forms. Having traced the assembly and the structure of the disk, the narrator stands at the threshold of the hottest zone, where the optically thick flow thins the corona, takes over, and photons begin to sample not only temperature and density, but also the curvature of space-time. The path remains inward toward the inner rings where time scales shrink. Spectral features bend and measurable imprints of strong gravity emerge in the form of broadened lines, rapid oscillations and reflection patterns that encode the spin and the depth of the potential well. At the scale just beyond circularization, the flow settles into a broad, cool, optically thick structure, whose task is to receive erratic parcels from the wake, smooth their differences, and pass mass inward with minimal fuss. This is the outer disk, a flat rotating sheet that presents a wide face to space
The
and a
filament
narrow edge to the
and the
orbit.
field.
Its outermost zones retain the memory of the incoming stream in the form of a diffuse impact arc, rather than a sharp point, because wind capture feeds from many angles. There, the gas arrives with a spread of speeds and directions
Where
collides
pressure
and
fails,
spreads around the rim.
fields prevail.
Shocks that form at these collisions dissipate kinetic energy into heat, and that heat rises through the vertical layers until it escapes as light. With each circuit around the rim, the residual irregularities of arrival are diluted, and the flow takes on the steady differential rotation set by gravity. In this region, the sound speed is low compared with the local orbital speed, so the disk remains thin. Its vertical thickness is a small fraction of its radius. Gravity from the black hole pulls the gas toward the midplane, while pressure pushes outward, and the balance produces a stratified atmosphere whose temperature increases from midplane to surface. Near the midplane, the density is highest, and those temperature is low enough that hydrogen is largely neutral, and molecules can survive briefly in the shadows of dust-sized grains. Higher up, the gas is warmer and partially ionized by radiation, both from within the disk and from the inner flow.
Come the seeds of
The
rebirth.
opacity that regulates
These
how
heavy
light
out-
escapes depends on temperature and composition. In these outer rings, absorption and scattering by ions and small
The
grains
dispersal of
dominate,
clusters.
so even
Watch
small
how
changes
open
in
clusters
temperature can
dissolve
alter
and
how easily
scatter,
radiation
leaving faint
diffuses
traces
outward.
of their origin.
Angular momentum must drift outward for mass to drift inward, and in the outer disk that transport is provided by magnetically driven turbulence that acts like an internal friction between neighbouring rings. The turbulence is not a random noise, it is a correlated
This is the
set of
dance of
motions
angular
sustained by
momentum.
weak magnetic fields in a
As
shearing
gas
flow.
rotates,
These motions convert a small fraction of orbital energy into heat and arrange a slow outward leak of angular momentum. The net effect is a gentle inward glide of matter, whose pace is set by how strong the turbulence becomes. Although this microphysics is hidden from direct view, the broad spectral shape of the disk's light and the slow viscous response of its brightness to changes in supply agree with the picture of a cool, optically thick outer flow governed by the magnetic stresses. The donor star rides nearby as a luminous neighbour and bathes the disk in ultraviolet light. That external illumination warms the surface layers and, together with radiation from the inner accretion region, keeps much of the outer disk in a warm state even when local dissipation dips. This heating suppresses large thermal
Energy in
runaways that would
translation.
otherwise dim
Trace
and
the journey
brighten
of
the disk
starlight as
by
it becomes
orders of
heat,
magnitude,
turbulence,
and it helps to
shadow.
explain why a wind-fed system with a small disk prefers steady output punctuated by modest flicker rather than long quiescent stretches and dramatic flares. Where the inner wake meets the rim, irradiation also changes chemistry. It dissociates fragile molecules, ionizes metals and puffs the upper layers, lifting a faint skin that can scatter light and imprint broad low contrast lines on the optical and ultraviolet spectrum. The disk is not a perfectly rigid plate. Because the mass arrives from a direction that is not exactly coplanar with the disk, and because radiation pressure from the inner regions pushes more strongly on any section that tilts toward the light, gentle warps can appear in the outer rings. Tidal forces from the supergiant also tug on the outer edge and set a truncation radius beyond which orbits are unstable. The combined effect is a disk whose outer boundary is rounded and slightly scalloped with a vertical height that varies with azimuth by a small amount. These warps remain subtle in this system because the orbit is not viewed edge-on,
The
and because
dust
the
acts as a
steady wind
filter,
supply
scattering
prevents
the
strong
blue starlight and
asymmetries from
allowing the
growing
warmer tones to
unchecked.
dominate.
But small,
causing the
slow
disk-
changes in the brightness of the outer disk over many orbits suggest that the surface breathes and nods in response to irradiation
By
and
utilizing
tide.
the hue,
A consensus
position, and
point
spectrum
at this
data from
radius
these
is
maps
that
of
the
color
outer
and
flow
motion,
is cool,
we uncover the
geometrically
universe's hidden
thin and optically
architecture.
thick, and that its behavior is governed by the steady exchange of angular momentum under magnetic turbulence. This picture is supported across many accreting binaries and
The
is
spiral
consistent
beneath
here
the
with
cross.
the stable continuum shape and modest state changes
The
observed.
foreground dust layer is separating
A lesser
cleanly now.
known detail specific
And the
to
velocity
wind-fed
data
systems
confirms
is
the
that the
shift in the
hotspot
CO
familiar
emission.
in stream-fed disks becomes a
Parallax
hot arc
provides
that
the first
spans a
rung on
wide
the
range of
cosmic distance
angles along
ladder.
the rim.
But to measure the
Because
truly
parcels
immeasurable,
arrive from the curved wake rather than a single nozzle, the heating is spread and persists over a larger sector, which softens orbital modulations in
Windows
optical
across
light
wavelengths.
and distributes the
From
liner
visible
emission
light
from the
to the
outer
pulsing
layers into a
energy of
broad
radio
crescent
waves,
rather than
the
a
heat
point.
signatures of
This geometry
infrared.
also seeds multiple
Follow the
vortices
21 centimeter
where the shear
line
is
as it
strongest
divides the
structures that
sky
may survive
into
for
layers
several
of
orbits
moving
before
gas.
being sheared apart, and that could imprint
molecules
gentle
in the
repeating
cold reveal
ripples in
how
the
carbon
optical flicker.
monoxide marks the
In
birthplaces
the
of new
vertical
stars
direction, the
within
outer
hidden
disk
filaments.
behaves like a radiating atmosphere supported by pressure from below and cooled by photons escaping through the surface. The midplane hosts most of the mass. Above it lies a warm, less dense skin where atoms are ionized and
This
line
high-temperature
emission
map
forms.
shows how X-rays chart
Because
the
the
immense
inner flow
energy of
shines
stellar
strongly in
explosions
high
and the
energy
powerful
light,
pull of gravity
the upper
combined.
layers also feel a rain of hard photons that heat small patches and carve shallow ionized cavities above the rim. As the binary turns, the line of sight crosses different chords through this layered atmosphere and through the translucent accretion wake that grazes the outer edge.
Deneb.
So narrow
The
absorption
luminous
features in
anchor.
ultraviolet light wax and wane with orbital phase. The outer disk leaks little mass to a wind at these radii because the escape speed is high compared with the local thermal speed, yet weak magnetically assisted evaporation may lift a thin veil of gas that drifts inward above the surface and feeds the corona indirectly.
These invisible
The rate of
magnetic
this
threads
evaporation,
channel
if
the
present,
diffuse
would
gas,
rise with the
shaping its slow
radiation
collapse.
and with the strength of
Radiation
magnetic
hard and
reconnection
soft.
in the upper layers,
Contrast
offering a
the
channel
harsh
by which
ultraviolet
changes
of
in
young
the inner
clusters
light can
with the
feed back
gentler
on the
glow
disk's
between
skin.
them.
The structure of the rim sets the conditions for waves that propagate
This is how
inward.
radiation sculpts
Spiral
the edges
density
of
waves
molecular
excited
clouds.
by the tidal pull of the companion run through the disk, as patterns that rotate more slowly than the gas. These waves steepen and dissipate, adding to the effective viscosity and modulating the inward mass flux. In systems with large, bright disks, such waves make clear signatures in Doppler maps. Here, where the disk is small and the line emission is weak, the same physics likely
Where shells
operates, but
become
leaves only
seas.
soft footprints
The
in the
expanding
continuum
fronts of these
and in the
supernova
timing of
remnants
small
ignite new rounds of
fluctuations.
star formation.
Even so, the presence of gentle quasi-periodic features in the optical flicker at timescales of hours to days is consistent with waves crossing the outer rings and with the relaxation of the rim after stronger clump impacts. An unresolved mystery in this region concerns the magnetic field that threads the outer disk. The captured wind carries its own weak tangled
dampening
field,
field held
and the
stable at
donor's
500
large-scale
GRC.
field, if present,
Radiation
may
scrubbers
drape
performed
around the
optimally.
disk and connect
Data
across the
acquisition is
wake.
complete.
How these external fields combine with the internal turbulence-generated fields is not yet measured. If external fields survive and link to the disk, they could enhance the outward
Brightness
transport
is
of
not
angular
nearness.
momentum and alter the threshold for launching a gentle thermally driven breeze from the surface. Observationally subtle polarization signals from the outer layers and delicate time lags between continuum and line emission would test this coupling, but current measurements are not yet definitive. Another uncertainty lies in the true three-dimensional shape of the rim where the wake meets the disk. Simulations
Faint
differ on whether the rim
filaments
hosts a
aligned with
single
magnetic
broad-standing
fields.
shock or a patchwork of transient
Echoes
shocks that
of
appear and fade as clumps arrive. Each picture predicts a different pattern of line widths and phase-dependent asymmetries, and distinguishing
The
between them
quiet
requires higher
geometry
cadence
of a
phase resolved
spiral.
spectroscopy than is usually available. The planetary scale perspective
Where
remains
density
visible even
becomes
here.
light.
Many such outer disks across the galaxy radiate softly and steadily, adding gentle ultraviolet and optical light to the interstellar background and seeding narrow zones of warming around their orbits. Their hard to soft radiation from inner regions filters through these cool edges and leaks into the diffuse medium, helping to maintain a low level of ionization in gas. Far from clusters, the metals locked in grains within these disks and released by sputtering in their surface layers feed the local dust economy. Though each disk is tiny compared with the surrounding star fields, their collective energy and matter exchange form one thread among many that keep the galactic plane in dynamic balance. In this system, the outer disk thus performs a quiet but essential service. It receives a variable wind supply and turns it into a
Starlight
steady
against the
inward
dark.
drift. It provides a broad cooling surface that radiates the byproducts of that smoothing. And it offers a gentle interface where radiation from the hot inner rings meets the cooler gas of the wake
and
and the
field.
wind. With these roles established and the physical state of the outer rings described, the narrator can move one step further inward toward the hotter radii where orbital speeds rise sharply, where radiation pressure comes to rival gas pressure,
Where
and where the
pressure
spectrum
fails,
shifts from optical and
fields
ultraviolet
prevail.
to soft X-ray light as the disk approaches the domain, where strong gravity begins to curve the paths of photons and matter alike. The narrator steps inward from the broad cool rings to the radii where orbital speeds climb, dissipation steepens, and the spectrum shifts towards soft X-ray light. Here the disk remains optically thick, geometrically thin, yet its temperature now rises rapidly with decreasing radius because each parcel of gas surrenders more orbital energy per unit mass as it falls deeper into the gravitational well. Differential rotation is extreme in a ring circle in minutes rather than hours, and the shear between neighbouring orbits feeds the same magnetically driven turbulence that transports angular momentum. Only now the power available to that turbulence is far greater. Dissipation heats the material and
From the
photons
ashes of
born in the
stellar
dense
death come the
midplane
seeds of
scatter and
rebirth.
absorb through
These
stratified
heavy
layers before escaping from a photosphere, only a small fraction of a radius above the plane. The light that emerges approaches
The
a color
dispersal
temperature of
clusters.
several million
Watch how
degrees,
open clusters
bright in
dissolve
soft
and
X-rays,
scatter,
with a
leaving
broad
faint
quasi-thermal
traces of their
shape set
origin.
by the integrated emission across many rings of different temperature. Irradiation from still deeper zones pours outward and warms the surface, while returning reflection light from the corona adds a faint hard veil to the spectrum. Vertical structure becomes crucial in these inner rings.
This is the dance of
Gas pressure
angular
still
momentum.
supports the midplane, but radiation
As gas
pressure now
rotates.
shares the load. In layers near the photosphere, photons exert a push that puffs the surface, making the local scale height slightly larger than in the outer disk. The increased thickness enhances the interception of hard photons, arriving from the corona and from the innermost rings, which in turn warms and ionizes the skin and strengthens certain emission and absorption features in the spectrum. Opacity is dominated by electron scattering at these temperatures, so photons random walk through many scattering events before they escape. Because scattering is nearly grey, the colour of the emergent light depends mainly on where absorption rather than scattering finally imprints a last thermalization. This depth shifts with temperature and density, subtly bending the continuum away from a perfect
Energy
thermal
in
curve.
translation.
The classic
Trace the
consensus
journey
in
of
this region
starlight
is that
as
a
it
thin,
becomes heat,
optically
turbulence,
thick disk
and
extends
shadow.
inward until general relativity sets a final stable orbit, and that viscous dissipation in these rings produces the soft thermal component observed in high-energy light. Many independent systems show this component brightening and hardening as the inferred inner radius moves inward, during softer intervals reinforcing the picture of a luminous hot inner disk that approaches close to the last stable orbit when the flow is dominated by the thin configuration. Even in this ordered structure, fluctuations remain. The supply from the outer disk wanders slowly as clumps are digested, and turbulence within the inner rings adds small rapid modulations. These combine into a broad spectrum of variability that places power on many timescales with characteristic humps where the disk responds most strongly. Thermal timescales on which heat is stored and radiated away are shorter here than in the outer disk because densities are high and distances are small. Viscous timescales on which mass drifts inward remain longer, but now fall within the range where sustained monitoring can see
The dust
gradual
acts as a
drifts in
filter,
flux
scattering
over
the blue
days to
starlight and
weeks.
allowing the warmer tones
The
to
surface
dominate,
layers coupled to the
causing the dis-
corona exchanging energy through Compton scattering and magnetic reconnection. When the coronal heating fraction rises, more soft
By utilizing
photons
the
are
hue,
upscattered,
position,
and the
and
disk
spectrum data from
appears
these maps
slightly
of color
cooler.
and motion,
Even if
we
the total
uncover the
power is
universe's
unchanged
hidden
because energy has
architecture.
been reallocated into a higher energy tail. When the coronal fraction falls, the disk grows brighter and hotter, and the soft peak strengthens. This push and pull
spiral
creates the
beneath the
familiar
cross.
alternation between harder and softer intervals seen in
There,
many
the foreground
accreting
dust
black
layer
hole
is separating
systems,
cleanly
though.
now.
In a steady
And the
wind-fed
velocity
case, the
data
swings
confirms
stay
the shift
modest
in the
and the
CO
soft
emission.
component remains present most of the
Parallax
time.
provides the first
Waves
rung on the
propagate
cosmic
through
distance
these
ladder.
rings.
But to
Spiral
measure the truly
patterns
immeasurable,
excited by
we
tides are weaker here than at large radii, but vertical and radial oscillations can travel as sound-like disturbances that modulate the emission.
Windows across wavelengths.
In some intervals,
From visible
narrow
light
features
to the
in the
pulsing
variability
energy of
spectrum
radio
appear at
waves,
frequencies
the heat signatures of
corresponding to
infrared
preferred timescales in
Follow
the inner
the
flow.
21-centimeter
Their
line
precise
as it
origin is
divides the
still
sky
debated,
into
but
layers
they
of
likely
moving
involve a
gas.
coupling between orbital motion,
Molecules in the
vertical
cold
breathing
reveal
modes
how
of the
carbon
disk, and
monoxide
precession of a
marks the
slightly
birthplaces of
tilted
new
inner
stars
region
within hidden
under the
filaments.
influence of frame dragging. If such precession occurs, it is gentle, and the resulting modulation only slightly wobbles the angle at which the corona sees the disk. The imprint would be small shifts in the balance of soft and hard light on
This
timescales much
high-temperature
shorter
map
than the
shows how
orbital period of
X-rays
the
chart the
binary,
immense
but
energy of
long
stellar
compared with the
explosions
local
and the
orbital
powerful
time in the
pull of
innermost
gravity
rings.
combined.
The chemical makeup of the gas entering these radii matters in subtle ways. The donor's wind is enriched in helium and shows signs of surface processing. As that material moves inward and heats, the exact electron-to-ion ratio and the abundance of intermediate mass elements alter cooling rates
the
and the
luminous
detailed
anchor.
opacity in the skin of the disk. A lesser known detail is that modest helium enrichment can slightly lower the depth at which the atmosphere thermalizes in soft X-rays, making the emergent spectrum just a little brighter at higher energies perceived for the same midplane temperature. The effect is
These
small
invisible
but in
magnetic
precise
threads
phase
channel the
resolved
diffuse
spectra.
gas,
It can
shaping
help
its
explain
slow
small
collapse.
offsets between the
Radiation
shape of the
hard
thermal
and soft.
continuum and simple
Contrast
models
the harsh
calibrated for
ultraviolet
solar
of young
composition
clusters
gas.
with the gentler
Magnetic
glow
fields
between them.
tangle through the inner
depth
rings
of
amplified by
ionization.
shear until they break and
This is
reconnect,
how
releasing
radiation
energy
sculpts the
impulsively.
edges of molecular
These
clouds.
reconnection events are candidates for feeding the hot corona perched above the disk. The geometry of that corona is partly encoded in the reflection spectrum. Hard photons plunge into the top layers of the disk, excite fluorescence and generate a broad iron feature whose shape is smeared and skewed by the orbital motion and by the curved paths that light
Where
follows near the
shells
black
become
hole.
seeds.
The breadth
The
of this
expanding
feature
fronts of these
indicates
supernova
that the
remnants
reflector
ignite
extends
new
very
rounds of
close
star
to the last
formation.
stable orbit. A higher reflection fraction suggests that the coronal source sits low and centrally concentrated, so that light has a better chance of striking the disk before escaping. A lower reflection fraction hints at a more elevated or patchy source. In this system, the observed balance favours a compact, centrally weighted corona during
The
harder
dampening
intervals,
field held stable
and a more
at 500
diffuse
GRC.
disk-hugging heat
Radiation
distribution
scrubbers
during
performed
softer
optimally.
ones.
Data
The reflection
acquisition is complete.
signatures also provide a measure of ionization in the skin, which rises with inner luminosity and changes the relative strengths of lines and edges. Radiation pressure can drive gentle
Brightness
vertical motions
is
in
not
the surface.
nearness.
Where the flux is highest, the photosphere lifts slightly, and where it is lower, the surface settles. These breathing motions occur on thermal timescales and can introduce soft correlated changes across neighbouring rings. If the inner disk is slightly tilted relative to the black hole spin axis frame, dragging adds a slow twist that makes the line of nodes precess. The combined effect could yield a quasi-periodic
Faint
change in the
filaments
observed
aligned
soft
with
light as the
magnetic
most
fields.
strongly illuminated sectors
Echoes
rotate
of
in and out of view, superposed on the broader variability set by clumpy feeding and coronal coupling. Observationally, such behavior
The
appears
quiet
as low amplitude
geometry of
coherent
a
signals in
spiral.
the power spectrum that drift in frequency as accretion conditions change.
Where density
Close to the inner edge, the
becomes light.
gravitational redshift becomes significant. Photons that climb out from these depths lose energy, shifting spectral features to lower frequencies and stretching the timestamps of rapid variations by small amounts. Orbital velocities reach a significant fraction of the speed of light, and Doppler beaming modestly enhances emission from sectors of the disk, rotating toward the observer while dimming those receding. The net result is a pattern of broadening and skewing that is well captured by the models of a relativistic disk. By fitting these models to the thermal continuum and to the reflection features, observers infer that the inner edge sits close to the theoretical limit set by a very rapidly spinning black hole, with the disk aligned to that spin. This inference is part of the consensus view in the literature on this system, and serves as a benchmark for comparing methods that read spin from light. Despite these advances, mysteries remain. One unresolved question is how a small, steadily supplied disk sustains a hot compact corona without large amplitude cycles. In large transient disks, state changes often track big swings in accretion rate and geometry. Here, the mean supply varies little, yet a persistent
pressure
coronal
fails,
component endures
fields
and keeps
prevail.
the spectrum from becoming purely thermal. Whether the heating arises mainly from magnetic reconnection in buoyant loops from vertical dissipation in a mildly thickened inner flow, or from weak shocks in a truncated two-phase region just inside the last stable orbit, is not settled. Each scenario leaves different fingerprints in the reverberation lags between the direct coronal light and the reflected response from the disk. The present data favour short lags consistent with a compact source near the axis, but the precision needed to map changes across orbital phase and spectral state is still developing. The planetary scale view returns even at this depth. The inner disk converts gravitational potential energy into radiation with high efficiency, and a fraction of that power escapes as hard photons that travel far beyond the binary. These photons
From the
ionize
ashes of
diffuse
stellar
clouds
death
in the
come the
galactic
seeds of
plane
rebirth.
contribute to heating of
These
the warm
heavy
interstellar medium, and when integrated over many such systems, help maintain a low level of excitation in gas far from
The
clusters of
dispersal of
massive
clusters.
stars.
Watch
The
how
inner
open
disk also
clusters
seeds
dissolve
weak
and scatter,
outflows, whether
leaving faint
in the form
traces
of a
their
faint
origin.
jet coupled to the corona, or as a radiation-driven breeze from the surface layers. These add a trickle of momentum to the local environment and carry a trace of processed material into surrounding space. Though small beside the output of the supergiant and neighbouring associations, these contributions are distinctive
This
in
is the
hardness
dance
and
of
variability,
angular
adding
momentum.
texture to the energy budget of the
As
region.
gas rotates,
With the inner disk now mapped as a luminous, optically thick engine, whose temperature, thickness and variability are set by the balance between viscous heating, radiative cooling and magnetic coupling to a compact corona. The narrator stands one step from the domain where the flow thins, where scattering dominates and where energetic electrons imprint a hard tail that flickers on the shortest accessible timescales. The path remains strictly inward, from the hot rings to the tenuous, very hot plasma above them, where soft photons are upscattered into hard X-rays, and where the signatures of strong gravity and rapid motion are written as timing and spectral structures in the high-energy light. Above the hot inner rings, the narrator enters a tenuous, very hot medium, where soft photons from the disk gain energy through repeated scatterings off
Energy
fast
in
electrons.
translation.
This is the
Trace the
corona,
journey
a
of
magnetized
starlight as
plasma
it
that
becomes
forms a
heat,
bridge between the
turbulence,
optically
and
thick
shadow.
flow and the hard X-ray light seen from the system. The corona is not a solid shell. It is a dynamic volume threaded by tangled fields that rise from the disk break and reconnect. Each reconnection event releases magnetic energy and heats electrons to temperatures of many tens to about 100 kilo-electron volts, high enough that a single scattering can lift a soft photon far up in energy. The emergent spectrum is therefore a smooth tail that extends beyond the thermal peak of the disk, curving with a characteristic hardness that reflects the balance between electron temperature optical depth and the rate at which fresh soft photons arrive from below. In intervals when the coronal heating fraction is large, this tail dominates the light. In intervals when heating slackens, the disk shines more strongly and the tail shrinks. The basic consensus here is that inverse Compton scattering in a hot optically thin plasma produces the hard X-ray continuum in accreting black hole systems, and that shifts in the power split between disk and corona. Explain the observed
The dust
alternation
acts as a
between
filter,
harder and softer
scattering the blue
states.
starlight
Geometry
and allowing
shapes
the
the
warmer tones
light.
to dominate.
If the
causing
heating
the dis-
concentrates near the axis in a compact region, soft photons from the inner ring see a bright lamp above them, and a large fraction of
By
hard
utilizing
photons
the
strike
hue,
the disk
position, and
and are
spectrum data
reflected.
from these maps of
The
color and
reflection
motion,
fraction
we
rises.
uncover the universe's
Reverberation
hidden
lags are
architecture.
short, and the iron feature from the inner surface appears strong and highly blurred. If the heating spreads into a patchy layer above the disk, fewer hard photons return to the surface,
The
lags
spiral
lengthen
beneath
slightly
the
and the
cross.
reflection fraction falls. Observations of this
There,
system
the
favour a
foreground dust
compact
layer is
centrally
separating
weighted
cleanly
source
now.
during harder intervals
And the velocity
and a
data
more extended
confirms the
disk
shift in the
hugging
CO
arrangement
emission.
during softer intervals.
Parallax
A
provides
pattern
the
that
first
fits
rung on the
naturally with
cosmic distance
changes in
ladder.
how magnetic
But to
energy is
measure the truly
deposited as
immeasurable,
accretion
we
conditions evolve. The corona does not float in isolation. It exchanges energy and particles with the upper layers of the disk,
Windows
evaporating
across
gas from the
wavelengths.
surface when
From visible
heating
light
is strong
to
and
the pulsing
condensing
energy
when
of
cooling
radio
by
waves,
soft
the
photons
heat
dominates.
signatures of infrared.
This exchange sets
Follow
the
the
coronal
21
density and
centimeter
optical
line
depth
as
and
it
can move the
divides the
boundary
sky
between
into
thin
layers
disk
of
and hot
moving
flow
gas.
inward or outward by a small amount.
Molecules in the cold
At the same
reveal how
time,
carbon
fluctuations in the
monoxide marks
supply
the
from larger
birthplaces of new
radii
stars
ripple
within hidden
inward through the
filaments.
disk and into the corona. Those fluctuations propagate on viscous timescales that shorten toward the center. So many small variations pile up and generate the broadband flicker that characterizes the light curve. The corona responds
This
quickly
high-temperature
because
map
its
shows
thermal
how
time is
X-rays
brief,
chart the immense
and the
energy of
combined
stellar
effect is a
explosion,
cascade
and the
of
powerful pull of
variability from
gravity
soft
combined.
to hard energies on timescales from fractions of a second to many minutes. Within this flicker, narrow features sometimes rise above the continuum of noise. These quasi-periodic oscillations appear as peaks at preferred frequencies that drift with spectral state and with luminosity. Though their detailed origin remains debated, one plausible family of models ties them to lens-throwing precession, a slow relativistic wobble of a slightly tilted inner flow around the black hole's spin axis. In such pictures, the coronal volume precesses as a whole, modulating the beaming pattern of hard
These
photons
invisible
and their
magnetic
illumination of
threads
the
channel
disk.
the diffuse gas.
The resulting
shaping its slow
oscillation
collapse.
imprints a small
Radiation
coherent
hard
signal
and
in both
soft.
the hard tail and
Contrast
the
the
reflection
harsh
features.
ultraviolet of young
The
clusters
frequency
with the
then
gentler
traces
glow
how far
between them.
inward the bright coronal
depth
region
of
extends,
ionization.
climbing when the inner edge moves
This is
closer
how
to the black
radiation
hole.
sculpts the edges
Other
of
models
molecular
invoke
clouds.
vertical breathing modes or standing waves in the hot flow. Distinguishing among them requires simultaneous timing and spectroscopic measurements with enough precision to track phase lags between continuum and reflection through the cycle. In this system, the signals are modest, yet they align with the broader behaviour seen across accreting black holes. As the spectrum softens, characteristic
Where
frequencies
shells become
rise
seeds.
and lag shorten,
The expanding fronts of
pointing
these
to a
supernova
shrinking and
remnants
cooling
ignite
coronal
new rounds
region
of
that
star
sits
formation.
closer to the disk. The corona couples naturally to outflows. When the spectrum is hard and the coronal power is high, a faint compact radio source brightens and reveals a steady collimated jet. Magnetic fields threading the inner flow are the likely driver. They tap rotational energy in the disk, and perhaps in the spinning black hole lift plasma,
The
along
dampening
open
field held
field
stable at
lines and
500
accelerate
GRC.
it to high speeds.
Radiation scrubbers performed
Even when the
optimally.
jet is weak,
Data
the tight
acquisition is
correlation
complete.
between radio power and hard X-rays hints that the same magnetic engine heats the corona and launches the outflow. When the spectrum softens and the thermal disk brightens, the radio
Brightness
source dims,
is not
suggesting that
nearness.
the jet base is quenched as field geometry and heating change. In transient state, transitions can produce discrete ejections. In this wind-fed, persistently accreting system, the changes are gentle and the jet remains a low, steady thread when present. The lesser-known detail is that at the lowest hard fluxes, very weak optical polarization with a preferred position angle has been reported in similar systems, a signature that, if confirmed here, would trace synchrotron light from the inner jet and fix its projected orientation relative to the disk. Seed photons for Comptonization come primarily from the inner disk, but a small contribution can arise from cyclosynchrotron emission within the corona itself if magnetic fields are strong. Such self-produced photons provide a baseline
Where
cooling
density
channel even when the
becomes
disk
light.
contribution dips, and can help stabilize the electron temperature against runaway heating. The photon balance therefore contains feedback loops. More seed photons cool the corona, softening the spectrum. A cooler corona intercepts fewer photons above the reflection threshold, altering the ion feature. A softer spectrum changes the ionization state of the disk's skin, which in turn modifies the reflection albedo and the pool of seed photons that return after one scattering. The observed spectra encode these couplings as subtle bends and lags that shift smoothly with state. The composition of the inflow can tune coronal cooling. Helium enrichment in the donor's wind raises the electron to ion ratio for a given mass inflow and slightly increases Compton cooling efficiency for the same heating rate, nudging the cutoff energy of the hard tail to lower values than would be expected for strictly solar composition gas. This effect is small and often buried under modelling uncertainties in geometry and heating, yet it offers one path to reconcile minor mismatches between simple Comptonization models and the softest observed hard tails in wind-fed binaries. Meanwhile, changes in the wind's clumpiness alter the soft photon supply indirectly
Where
by
pressure
modulating
fails,
the inner disk
field
brightness on
prevails.
short timescales, and those modulations appear as mirrored, slightly delayed echoes in the coronal light, a local form of reverberation that rides atop the broader variability. A central uncertainty remains the exact topology of the coronal magnetic field and the mechanism that sustains heating at a roughly constant level for long intervals. Does the energy arrive in many small reconnection events randomly distributed over the inner rings, or in fewer larger releases near the axis, where fields from opposite sides of the disk collide? Does the coronal volume form a continuous layer or a swarm of magnetically supported buoyant loops that rise, flare, and sink? Each topology predicts different patterns of microflares and different coherence in the hard tail. High time resolution observations that search for nanoflares and map energy-dependent lags are beginning to probe this regime, but the answers are not yet settled. Another open question is whether a weak radiatively driven wind leaves the inner disk surface in softer intervals, adding a cooler scattering layer between disk and corona. Such a layer would imprint narrow absorption lines in the soft X-rays blue shifted by modest speeds and could partly shield the outer disk from the harshest photons, changing the ratio of direct to reflected light. The corona also shapes the reflection spectrum that carries direct signatures of strong gravity. Hard photons that strike the inner disk are bent by space-time, and the returning light is shifted and blurred before it escapes. The breadth and skew of the iron feature, therefore, measure how close the reflecting surface approaches the black hole and how fast the inner rings turn. In this system, the reflection profile points to an inner disk that reaches almost to the innermost stable orbit and to a black hole that spins very rapidly. The reflection fraction suggests that during harder intervals, the coronal source sits low within only a few gravitational radii above the axis, while during softer intervals it spreads and lowers its compactness. These inferences provide one of the cleanest examples of reading geometry and spin from light in a persistent wind-fed binary. On a planetary scale, the coronal photons escape the system and travel widely through the galactic plane. Their high energies allow them to penetrate diffuse gas, maintain
Energy
small
in
ions
translation.
in higher charge
Trace
states,
the
and
journey
add
of
gentle
starlight
heating
as
far
it
from
becomes
star-forming
heat,
clusters.
turbulence, and shadow.
The intermittent jet tied to the coronal engine injects a thin thread of momentum into the surrounding medium, and seeds faint magnetic structure on scales larger than the binary. The combined effect is small in any one system, but integrated over the population of high-mass X-ray binaries in the galaxy, becomes a measurable ingredient in the thermal and ionization balance of the interstellar environment. With the coronal geometry heating and coupling to reflection and outflow now outlined, the path remains strictly inward. The narrator advances to the very inner rings where strong gravity leaves its sharpest imprint on the spectrum, and timing, the domain of relativistic reflection in iron and neighbouring lines, where curved space-time skews features, time delays, echo across light seconds, and the shape of the innermost stable orbit encodes the spin and orientation of the black hole that anchors the flow. The narrator now occupies the region where the inner disk and the corona converse in light, and where curved space-time imprints its grammar on that conversation. Hard photons from the hot, tenuous corona
The
rain
dust
upon
acts
the
as a
very
filter,
hot, optically
scattering the
thick
blue
rings,
starlight and allowing
and are
warmer
absorbed,
tones to
scattered, and
dominate,
re-emitted as
causing the
reflection spectrum. This spectrum carries a handful of hallmark features. Foremost among them is a blend of iron
By utilizing
fluorescence
the
and
hue,
adjacent
position, and
lines that in
spectrum
a
data
calm
from these
Newtonian
maps of
world
color and
would
motion,
appear as
we
narrow
uncover the
symmetric
universe's
peaks.
hidden architecture.
Here, deep in the gravitational well, the feature broadens and skews. Doppler shifts from orbital motion smear the line to both higher and lower energies, while
The spiral
gravitational
beneath the
redshift
cross.
pulls the whole profile toward lower energies. The
There,
side of the
foreground
disk
dust
moving
layer is
toward the
separating
observer
cleanly now.
is modestly brightened
And the velocity
by
data
beaming.
confirms the shift in
The
the CO
side
emission.
moving away is dimmed, and the
Parallax
aggregate
provides
curve
the
takes
first
on a
rung on
long,
the
soft
cosmic
tail
distance
that
ladder.
stretches far below
But to
the
measure
rest
the
energy
truly
of iron.
immeasurable,
This
we
is the signature of relativistic reflection, and it announces how close the reflecting surface approaches the black hole and how fast the inner rings turn. A consensus point at this depth is that the breadth and skew of the iron complex, together with the shape of the hard reflection continuum, known as the Compton hump, around a few tens of kilo electron volts, require a reflector extending to radii comparable to the innermost stable circular orbit. When the continuum is modelled with a compact coronal source above the axis, often called a lamp geometry, and the reflection is computed in a space-time set by a rapidly spinning black hole, the observed profile is reproduced with an inner radius that lies very near the theoretical limit for prograde
This
orbits.
high-temperature map
The
shows how
same
X-rays
models
chart
tie the
immense
emissivity,
energy
the
of
radial
stellar
distribution of
explosions and the
reflected
powerful
power,
pull of
to
gravity
the height and
combined.
compactness of the coronal source. A low bright source concentrates illumination on the inner rings and steepens the emissivity, strengthening the relativistic blurring. A higher, more diffuse source flattens the profile. In this system, the reflection fraction rises when the spectrum hardens, implying a low coronal height and strong light bending that returns more hard photons to the disk. During softer intervals, the reflection fraction drops and the blurring eases slightly, consistent with a more extended heating region that wraps over the inner surface. Time adds a second dimension to the measurement. Hard photons strike the disk and then re-emerge after a light travel delay, and a brief residency in the heated skin. These reverberation lags are short, measured in fractions of a second for inner radii of only a few gravitational lengths, and they depend on energy, because each part of the reflection spectrum forms at a slightly different depth and radius. In practice, the lag as a function of energy shows a small bump near the iron band and a broader rise across the energies of the Compton hump. The narrator reads these lags as echoes that locate the coronal source and the reflecting surface in 3 dimensions. Shorter lags point to a lower height and a closer reflector. Longer lags point to a higher, more diffuse source. In this binary, the lags remain small even when the spectrum softens, reinforcing a picture of a reflector that stays near the inner limit and of a coronal source that never rises far from the axis. Reflection also measures the state of the surface. The ionization parameter, a ratio that compares ionizing flux to gas density, controls which ions of iron and neighboring elements are present in the skin. When the inner disk brightens, the surface becomes more ionized. The iron line shifts in detailed shape and soft
Radiation
excess
scrubbers
emission from
performed
many
optimally.
blended lines grows.
Data acquisition is complete.
The density of the skin matters too. At very high densities, free processes and collisional effects alter the soft part of the reflected spectrum, raising a smooth
Brightness
pedestal beneath
is
the iron
not
features.
nearness.
A lesser known detail in wind-fed, high-mass systems is that the outer supply can enrich the surface with helium and slightly change electron densities for a given mass column. That change, although subtle, pushes the detailed balance of heating and cooling in the skin, and can explain why the soft excess at lower energies is sometimes stronger than simple low-density reflection models predict. Accounting for higher density reflection brings models and
Faint
data into
filaments
closer agreement
aligned with
without
magnetic
adjusting the
fields.
geometry. Geometry is further
Echoes
probed by
of
how the reflection responds as the hardness of the continuum drifts. When the source hardens, the iron feature strengthens relative to the direct continuum.
The quiet
The Compton hump
geometry of a
grows, and the
spiral.
fitted emissivity index at small radii often steepens, as if more light bends down onto the inner surface. When the source softens, the iron feature weakens, and the hump relaxes and lags, shrinks slightly as the coronal compactness falls. These coordinated shifts support the light-bending picture in which a low source both enhances reflection and reduces the fraction of hard photons that escape directly to the observer. The same coupling is mirrored in the relation between hard X-ray power and the faint compact radio core when light bends strongly and reflection is high. The radio source brightens, consistent with a geometry where magnetic energy near the axis powers both coronal heating and the base of a weak jet. The reflection spectrum also constrains the inclination of the disk. Higher inclinations, meaning larger tilt relative to the line of sight, broaden the line by boosting the Doppler contribution and enhance the
Starlight
blue horn
against the
from the
dark.
approaching side. Lower inclinations narrow the profile. In this system, independent orbital constraints limit the inclination to a moderate angle, and reflection fits agree supporting a
filament
self-consistent
and the
geometry
field.
in which the disk plane aligns with the orbit to within small errors. Any residual misalignment would introduce nodal precession of the inner flow through frame dragging, and might imprint slow changes in the reflection shape or in the phase of reverberation
Where
lags.
pressure fails,
Hints of such
fields
behaviour exist
prevail.
in the gentle drift of characteristic frequencies but remain below firm detection. An unresolved mystery centres on the precise topology and longevity of the coronal source that drives the reflection. Does the heating occur in a single compact region near the axis, or in many small transient patches that flare and fade above different azimuths? A single lamp would produce very uniform illumination patterns and very stable lags. A patchy corona would imprint grainier time-dependent illumination with small energy-dependent shifts in lag and line shape that wander on timescales of minutes. Present measurements show smooth behaviour averaged over many cycles, but the microstructure remains hidden. Another open question concerns returning radiation, the fraction of reflected light that is bent by spacetime back onto the disk, especially for very high spin.
From the
This
ashes of
feedback
stellar
can
death
amplify
come
inner
the seeds of
illumination and
rebirth.
subtly reshape the
These heavy
spectrum. Evidence in similar systems hints at its presence. When the iron feature appears stronger than the direct coronal power would
The
imply,
dispersal of clusters.
whether the same
Watch how
enhancement is
open
operating
clusters
here is
dissolve and
plausible but
scatter,
not yet
leaving
isolated
faint
uniquely
traces
from
of their
changes in
origin.
height and compactness. Polarization offers a complementary angle on geometry because scattering in the disk and in the coronal medium aligns electric vectors and gravity bends their paths. In the hard state where coronal light is strong and reflection is prominent, one expects a modest polarization
This is the
fraction that
dance of
rotates with
angular
energy
momentum.
across the iron feature and the Compton
As
hump.
gas rotates,
Measuring such small signals in a bright, steady wind-fed system is hard, and existing limits remain coarse. If future instruments resolve a rotation of the polarization angle through the iron band, that rotation would fix the orientation of the inner disk on the sky and test whether the coronal source sits above the axis or is spread in a slab. From a broader standpoint, the reflection spectrum ties the microphysics of plasma and radiation to the macroscopic attribute of spin. In this system, the inner radius inferred from the breadth of the iron feature and from the thermal peak during soft intervals lies very close to the limit allowed by a rapidly rotating black hole aligned with the disk. This alignment may have been present at birth if the compact object formed in a quiet collapse with little kick, or it may have been maintained by steady torque from a symmetric
Energy
wind-fed flow.
and translation.
Whether the
Trace
near
the journey
maximal
of
spin is
starlight
natal
as it becomes
or the
heat,
result of long
turbulence,
slow
and
feeding
shadow.
remains uncertain, because wind-driven disks are small and may not carry enough angular momentum over the lifetime of the system to spin the hole up dramatically. Nonetheless, the current evidence supports a high spin and shows how reflection acts as a clean translation between geometry in curved spacetime and features in the spectrum. On planetary scales, the photons that participate in reflection do not all vanish into modelling. They stream outward and add hard light to the galactic plane. Each reflection event reshapes the spectrum of escaping photons, making it richer in energies that penetrate diffuse gas. Integrated over many such binaries, this process raises ionization fractions in warm clouds and influences the chemistry of species that require energetic photons to form or to remain in excited states. The very short reverberation lags also mean that the high-energy environment flickers on light-second scales, and although the surrounding medium blurs these fluctuations, a remnant of that rapid flicker remains in the glow of gas near the binary, a subtle
The dust acts
high-frequency
as a
texture
filter,
in the otherwise
scattering the
steady
blue
radiation
starlight and
field of
allowing the warmer
massive star
tones to dominate,
associations. With
causing
the
the
relativistic mirror now red, the narrator keeps the path inward. The remaining step is to the tightest orbits permitted by gravity
By utilizing
and
the
to the
hue,
meaning of a
position, and
last
spectrum
stable
data
ring,
from these maps of
the
color and
domain where
motion,
the disk
we
gives
uncover
way
the
to
universe's
plunge,
hidden
where
architecture.
stable circular motion ends, and where the black holes spin and the geometry of space-time decide how efficiently mass turns to light before crossing the event
The
horizon.
spiral beneath
There,
the
the
cross.
innermost edge and the rate at which matter spirals past
There,
it set
the
the
foreground
efficiency
dust
of the
layer is
engine and
separating
close the
cleanly
chain
now.
from large-scale wind
And
to
the velocity
deepest
data
gravitational
confirms the
well in the
shift in the
system.
CO emission.
From the mirrored inner rings, the
Parallax
narrator
provides
turns
the
to the
first rung on
slender
the
structures
cosmic
that leave
distance
along the
ladder.
rotation axis,
But to measure the
where
truly
magnetic fields and
immeasurable,
rotation
we
couple the disk, the corona and the black hole to a collimated outflow. A compact jet in this context is a steady,
Windows
mildly
across
relativistic
wavelengths,
stream
from
that
visible
carries
light
energy
to the
momentum
pulsing
and
energy of
magnetic
radio
flux
waves,
away from the
the heat
innermost flow.
signatures of infrared.
It is faint compared
Follow
with the
the
brilliance of the
21
X-rays,
centimeter
yet
line as it
persistent enough
divides
that
the
careful
sky
radio
into
maps
layers
resolve a
of
core
moving
only
gas.
milliseconds across,
Molecules
with
in
hints
the
of
cold
extension
reveal how
aligned along a
carbon
stable
monoxide
position
marks
angle.
the birthplaces of new
The
stars
consensus
within
picture
hidden
is that a
filaments.
jet forms when large-scale magnetic fields thread the inner disk and the region just above it. Rotational shear wins the field into a helical shape. Magnetic pressure lifts plasma, and electric fields generated by the twisting bundle accelerate particles.
This high
Two
temperature
complementary
map shows how
channels may
X-rays
operate
chart the
together
immense
where
energy of stellar
one taps
explosions
orbital
and the
energy from
powerful
the inner
pull of
disk,
gravity
launching
combined.
plasma along open field lines that flare from the surface. The other taps rotational energy from the spinning black hole itself, coupling the horizon to distant space through magnetic tension. Which channel dominates is set by field strength spin and the geometry of the inner flow,
The
but
luminous
both
anchor.
require ordered flux to be dragged inward and concentrated near the axis. The jet does not switch on and off randomly. It follows the state of the inner accretion flow. When the spectrum is hard and the coronal power is high, the radio core brightens and the outflow appears. When the spectrum softens and the thermal disk wins,
These
the radio
invisible magnetic
fades, which
threads
observers
channel the
describe as
diffuse
quenching
gas,
of the jet.
shaping its slow collapse.
In this wind-fed
Radiation
system, the
hard
changes
and
are
soft.
gentle rather than abrupt,
Contrast the
yet
harsh
the coupling
ultraviolet
holds
of
harder
young
intervals
clusters with
correlate
the
with
gentler
stronger
glow
radio,
between them.
and the relation
The
between
depth
hard
of
X-ray
ionization.
luminosity and radio flux follows a track
This is how
consistent with
radiation
other
sculpts the
accreting black
edges of
holes.
molecular clouds.
The compact core shows a flat to slightly inverted spectrum at centimeter wavelengths, a signature of overlapping self-absorbed synchrotron zones along the flow, each with its own turnover frequency. Closer to the engine at millimeter and infrared bands, the spectrum steepens where the jet becomes optically thin and the most energetic electrons
Where
dominate
shells
the emission.
become seeds.
This break shift
The
with
expanding
accretion
fronts of
conditions,
these
sliding to
supernova
higher
remnants
frequency
ignite
when
new
the jet
rounds
base
of
is
star
hotter and
formation.
denser and receding when the base cools. The jet does not traverse empty space. It drills through the donor's wind, and the surrounding ionized gas absorbs low-frequency radio light by free processes. As the binary orbits, the path through the wind changes, modulating the observed radio flux and rendering the outflow fainter at phases where the
The
line of
dampening
sight
field held
crosses denser
stable at 500
columns.
GRC.
This
Radiation
orbital
scrubbers performed
modulation is a
optimally.
lesser-known
Data
detail
acquisition is
that
complete.
confirms how intimately the jet and wind interact on scales only a few times the orbital separation. It also explains why the core position on the sky
Brightness
shifts slightly,
is
with
not
observing
nearness.
frequency lower frequency emission forms farther downstream, where the
quiet
jet has expanded
geometry
and the
of a
optical depth has
spiral.
fallen, an effect called core shift. Measuring this
Where
offset
density
at many
becomes
frequencies
light.
fixes gradients of magnetic field and particle density along the flow, and reveals how quickly the jet loses pressure and brightness with distance from the engine. Magnetic fields organize the jet and set its degree of order. Synchrotron emission is
Faint
polarized,
filaments
and the
aligned
orientation
with
of the
magnetic
polarization
fields.
vector maps the field projected on the
Echoes of
sky. In compact, steady jets, the polarization fraction is small. because many turbulent cells with different field directions contribute, but weak preferred alignments still emerge. The position angle of this weak polarization stays close to the jet axis, tying the radio core and the inner disk geometry together across long intervals. Faraday rotation in the wind and in the immediate environment rotates the polarization angle, with wavelength a probe of the line of sight magnetic field and electron density. The measured rotation is modest, consistent with the magnetized ionized medium in the cavity carved by the wind and the X-ray source. These signatures reinforce the picture of a jet that is magnetically dominated near launch and that gradually shares energy with particles as it spans. Particle acceleration along the jet occurs in standing shocks and in zones where magnetic reconnection releases stored energy. Electrons gain a power law distribution of energies, and their synchrotron radiation carries this input. The highest energy electrons cool quickly, so the surface spectrum steepens downstream where only longer-lived lower energy electrons remain. Inverse Compton scattering of stellar photons by jet electrons can add a faint high energy component at gamma ray energies, though in this system the dense photon field and modest jet power limit such emission to levels that are hard to separate from the coronal tail. The composition of the jet remains uncertain. If baryons are present in large numbers, the kinetic power for a given radio brightness is higher than if pairs dominate. Observations of moving features and constraints from broadband spectra do not yet decide the balance between electron-proton plasma and electron-positron pairs. This unresolved question matters because composition controls how momentum couples to the ambient medium and how far the jet propagates before it disperses. Close to the engine, the jet base overlaps the coronal volume. The same magnetic loops that heat electrons above the disk may feed the base by opening and reconnecting. As accretion softens and the thin disk brightens, field geometry appears to shift toward configurations that trap energy locally rather than vent it upward, and the jet weakens. As accretion hardens and the corona compacts field lines open and guide plasma outward, restoring the radio core. The timescale for these changes is short, indicating that the base responds quickly to the balance between heating and cooling in the inner flow. Reverberation lags that place the coronal source only a few gravitational radii above the disk imply that the launch region sits within light seconds of the reflector, a tight spatial coupling between the lamp that illuminates the disk and the nozzle of the jet. The large-scale fate of the outflow depends on the opposition it meets. In regions where the donor's wind is strong, the jet is confined and bends slightly as it trades momentum with the surrounding flow. On larger scales, as the wind thins, the jet can inflate a faint elongated bubble of synchrotron emitting plasma in the interstellar medium. In persistent systems, this bubble grows slowly, storing the integrated kinetic power of many years of steady outflow, and fades into the background after the engine switches off or weakens. The impact on the surrounding gas is modest compared with the radiation from the supergiant, yet the jet's momentum and magnetic field seed-ordered structure that outlasts the current accretion state. The planetary scale observation is that many such small jets across the disk inject magnetized plasma into the interstellar environment, contributing a distributed low-level input of energy and ordering that complements the dominant feedback from massive stars. Jet power scales with accretion rate and with the magnetic flux accumulated near the black hole. If the inner flow drags inward a field strong enough to approach a magnetically arrested configuration, the jet can carry a large fraction of the accretion power. In a wind-fed system, the supply of ordered flux likely varies with the structure of the donor's wind and with the history of clump capture. Periods of enhanced capture could briefly load the inner disk with stronger fields and raise jet power. Periods of quieter supply could do the opposite. These slow drifts would appear as long-term trends in radio brightness, not strictly tied to the short timescale X-ray variability. The presence of very high spin inferred from reflection suggests that the black hole
The
can in
dust acts as a
principle
filter,
donate rotational
scattering the
energy
blue
to the
starlight
jet
and
if the
allowing
field
the warmer tones
configuration
to dominate.
allows. Whether this
Causing the
contribution is significant in steady low-power jets remains under study, another unresolved piece in the coupling between spin field
By
and
utilizing the
outflow.
hue,
The
position,
jet
and
also
spectrum
imprints
data from
itself
these
in
maps
subtle
of color and
timing
motion,
links.
we uncover
Rapid
the
hard
universe's
X-ray
hidden
variations
architecture.
sometimes lead radio changes by short delays consistent with the travel time for disturbances to propagate from the base to the region where radio becomes optically thin. These lags are small because the compact core lies only a short distance from the engine.
There, the
They
foreground
support
dust
a
layer is
physical
separating
picture
cleanly
in
now.
which fluctuations
And
in
the
coronal
velocity data
heating
confirms
modulate
the shift
particle
in the CO
injection into
emission.
the base, which then drift
Parallax
outward and
provides
brighten the
first
radio a
rung
few
on the
moments
cosmic
later.
distance ladder.
In
to
turn,
measure the
orbital
truly
modulation by the wind
immeasurable,
can mask or reveal parts of this link, so only after averaging many cycles does the relation stand out clearly. Viewed from the vantage of the inner accretion sequence, the jet is the final pathway that matter and magnetic energy take when they do not radiate away and mark the disk. Most of the gravitational energy becomes light in the inner rings and corona, but a fraction leaves as kinetic and magnetic flux along the axis. That fraction is small in absolute terms, yet critical for completing the energy ledger and for understanding how accretion states map to outflows. The jet's steady presence during hard intervals, its fading, during soft intervals, its polarization that tracks a stable axis, its
This high-temperature map
frequency-dependent
shows
core
how
position,
X-rays chart the
set
immense
by
energy
optical
of stellar
depth and its
explosions
slight
and the
orbital
powerful pull of
modulation by the
gravity
donor's
combined.
wind together, compose a coherent set of signatures that fix its geometry and its coupling to the engines. With the role of magnetism and outflow established, the path remains inward but now bends from flow that leaves to flow that circles at the very edge of stability. The narrator approaches the last permitted orbits where the innermost stable ring sets the efficiency of the engine, where plunging motion begins, and where the absence of any solid surface defines the limits of what light and matter can reveal about the horizon that lies just beneath. The narrator now reaches the threshold where ordered rotation meets the limit set by curved space-time, the band of radii where circular motion remains stable only down to a last permitted ring, and where spin decides how tightly the flow can turn before it plunges. This inner marker is the innermost stable circular orbit, a radius defined not by pressure or magnetic forces, but by geometry within it. No small push or radiative loss can be balanced by a slightly tighter circle because there are no stable circles left. The position of this radius depends on the spin of the black hole and on the alignment between the spin axis and the direction of orbital angular momentum in the disk. For a non-rotating case, the last stable orbit lies farther out. For a rapidly rotating case with the disk turning in the same sense as the spin, the orbit moves inward to only a few gravitational lengths from the center. The closer this ring sits, the deeper the potential well that the gas can explore before it must fall, and the higher the efficiency with which gravitational energy can be turned into light in the rings above the edge. In the system under study, multiple lines of inference point to a last stable orbit that lies very near the inner limit, allowed by a high prograde spin, and that placement explains the presence of very hot thermal emission in softer intervals and of strongly blurred reflection features whose tails extend deep to lower energies. The disk does not end abruptly at this radius as if cut with a blade. The surface density and pressure fall inward, the orbital shear steepens, and the flow begins to lose its ability to maintain circular balance. Small perturbations that would be damped or healed at larger radii grow instead, and gas starts a gradual transition from nearly circular motion to a plunging path that threads the narrow gap between the last stable ring and the horizon. This transition region is thin in radial extent
Faint
but
filaments
powerful in
aligned
effect.
with magnetic
Angular
fields.
momentum no longer moves outward
Echoes of
efficiently because orbits no longer communicate across stable circles. Dissipation drops, cooling changes, character and radiation
The quiet
emitted.
geometry
Here is
of a
strongly affected
spiral.
by the redshift and by the bending of light. Photons that do escape carry a
density
final
becomes
skewed
light.
imprint of the last orbits. Photons that do not escape carry heat across the horizon and do not return. The disk just outside the edge still dictates much of what is seen, but the properties of the flow inside the edge set the precise shape of the faintest, most redshifted parts of the reflection spectrum, and the exact location of the peak of the thermal light during the softest intervals. In a steady picture, the inner edge of the optically thick disk hugs the last stable orbit. In more dynamic pictures, magnetic fields that thread the inner rings can bridge part of the plunging region and transmit stress inward, altering the classical boundary conditions. If such magnetic coupling persists, a small fraction of angular momentum and energy can still be transferred across the edge, changing the local dissipation profile and slightly shifting how the
Starlight
reflected
against the
light is
dark.
distributed with radius. The magnitude of this effect in a thin, bright disk remains a topic of study, but the current set of observations favours an inner edge very
The
close to the
filament
theoretical limit
and
for
the
high
field.
spin, with only modest deviations that can be accommodated by a weak stress extending a little inside the edge. Frame dragging, the twisting of spacetime by a spinning mass, operates strongly in this zone. Orbits that are
Where
not exactly
pressure fails,
equatorial precess with their
fields
nodes
prevail.
sliding around the spin axis. If the disk's angular momentum at large radii is not perfectly aligned with the black hole viscous torques, communicate this misalignment inward while frame dragging twists the inner rings. The competition produces a configuration in which the inner disk aligns with the spin, while the outer disk remains in its original plane connected by a smooth warp. This Bardeen-Peterson-like behaviour is gentle in a thin luminous disk and likely remains hidden below the sensitivity of current timing and spectral measurements here. But its presence in principle explains how an initially small tilt can be erased near the edge, while the broader binary plane remains unchanged. The precession frequency set by frame dragging rises steeply as radius falls, so any slight wobble of the inner flow could in principle leave narrow timing features whose frequency shifts with the inner radius. Hints of such
From the
behaviour in
ashes
the
of
hard
stellar
tail
death
have been
come
read
the
as
seeds of
signatures of a
rebirth.
slowly changing
These
coronal
heavy
geometry, coupled to a very compact inner disk that grazes the last stable orbit. Efficiency
The
is a
dispersal
key
of
metric at
clusters.
this depth.
Watch how open
The
clusters
fraction of rest
dissolve
mass
and scatter,
converted to
leaving
radiation
faint
in a
traces
thin
of
disk
their origin.
equals the binding energy per unit mass at the last stable orbit, and that fraction climbs as the orbit moves inward with higher spin. For high prograde spin, the efficiency can reach values that are several times those of non-rotating cases. In practice, wind-fed disks
This
like
is
this
the
one
dance of
radiate with
angular
efficiencies
momentum.
influenced by additional factors such as
gas
coronal
rotates.
power, returning radiation and mild stresses inside the edge, but the floor is set by geometry. The observed luminosity, when combined with the inferred mass inflow rate from wind capture models, and with the distance aligns with a high efficiency scenario, strengthening the case that the last stable orbit lies close in and that spin is large. The innermost temperature and the shape of the thermal continuum during soft intervals carry the same message fits that assume a disk, truncated far outside the last stable orbit, fail to reproduce both the colour and normalisation of the soft light, while fits that allow a small inner radius and higher spin succeed with consistent inclination and distance. The angular momentum budget near the edge closes with magnetic stresses, radiation and turbulence. Magnetic fields generated by shear can buoyantly rise from the inner rings, reconnect and feed the
Energy
corona.
in translation.
Other field lines are
Trace
dragged
the
inward
journey
and
of
stretch
starlight
across
as
the
it becomes
plunging
heat,
region, possibly
turbulence,
tapping additional
and shadow.
shear. Turbulence remains subsonic in the thin disk but approaches transonic conditions as the flow loses circular support. Radiation carries away energy, but because of strong redshift contributes less to what is seen from the deepest layers than to what is seen from just outside the edge. A lesser known detail is that the density at the photosphere right above the last stable ring may rise to values where free heating and cooling alter the soft end of the reflection spectrum. Accounting for such high density effects refines the fit to the iron band and the underlying continuum, and reduces the need to invoke unusual abundances to explain a strong soft excess. Another subtlety concerns returning radiation. A fraction of photons emitted upward from the inner rings are bent back toward the disk by gravity striking the surface again and deepening the illumination of the very inner annuli. This feedback steepens the emissivity profile and amplifies the relativistic smearing without changing the total coronal power, and its strength grows with spin because stronger curvature returns more light. The last stable orbit also frames the smallest dynamical timescales
By
accessible
utilizing
to
the
the disk.
hue, position, and spectrum
Orbital
data from
periods
these
at
maps
these
of color
radii
and
drop to
motion,
milliseconds
we uncover
for
the
stellar
universe's
mass
hidden
black
architecture.
holes, far shorter than any timescale set by the binary orbit or by the feeding wind. Variability on such short times carries the imprint of processes anchored at the edge. Small coherent oscillations can arise
There,
from
the
vertical
foreground
breathing
dust layer
modes of
is
the
separating
inner
cleanly
rings,
now.
from
And the
corrugation
velocity
modes that
data
ripple the
confirms the
surface,
shift
or
in the
from
CO
precession
emission.
of a slightly tilted
Parallax
inner
provides
flow.
the first rung
In the
on
present
cosmic
system,
distance
where the
ladder.
accretion rate is
But
steady
to
and the
measure the
corona
truly
remains
immeasurable,
present,
we
the broad noise dominates and any narrow signals appear with small amplitude. Yet their characteristic frequencies cluster in the range
Windows
expected
across
for
wavelengths,
dynamics near the
from
last
visible
stable
light
orbit,
to the
and
pulsing
drift
energy
upward
of radio
as the
waves,
spectrum
the heat
softens
signatures
and
of
the inner
infrared.
disk brightens,
Follow the
suggesting a
21
slight inward
centimeter
move of
line
the
as it
effective inner
divides the
radius within
sky
the same
into layers of
high-spin
moving
geometry.
gas.
An uncertainty that
Molecules in the
persists
cold
is the
reveal
exact
how
amount of
carbon
stress
monoxide
transmitted
marks the
inside the last
birthplaces of new
stable orbit
stars within
in
hidden
real
filaments.
magnetized radiating disks. Simulations show that magnetic fields can carry torque inward, and that some dissipation can occur in the plunging flow, but the degree to which this alters spectra in thin, high-luminosity disks remains debated.
This high-temperature
Observationally
map
small
shows how
differences
X-rays
between
chart the
models that
immense
assume
energy of
zero
stellar
stress at the edge
explosions and the
and
powerful
models that
pull of
allow
gravity
modest stress
combined.
can often be absorbed by slight changes in spin and inclination when fitting data of limited precision. As instruments improve and as high cadence phase resolved spectroscopy advances, it may become possible to break this degeneracy and measure the stress profile directly through the finest
the
details of the
luminous
iron
anchor.
band and through subtle shifts in reverberation lags. Another open question is how often the inner disk achieves complete alignment with the black hole spin in wind-fed binaries. If alignment is common and persistent reflection fits should find inclinations that match the binary plane. If not, small
These invisible
misalignments should
magnetic
appear as
threads
slow
channel the
secular
diffuse
drifts in the
gas,
shape of
shaping its
reflection
slow
features and
collapse.
in the phase of
Radiation, hard
quasi-periodic
and
signals
soft.
linked to precession.
Contrast the harsh
Current
ultraviolet of
indications
young
here
clusters
favour
with the
close
gentler
alignment,
glow
but long
between them.
baselines are needed to
Depth
rule
of
out gentle
ionization.
drifts. On planetary scales,
This
the
is how
efficiency set by the
radiation
last
sculpts the
stable
edges
orbit
of
governs
molecular
how much of the
clouds.
captured wind's rest mass is returned to the surrounding medium as light. High spin thus raises the fraction of power that escapes as radiation, rather than being swallowed as heat, increasing the number of hard photons available to ionize diffuse gas and to maintain other high charge states in species that are sensitive to X-rays. The smallest radii also control how much
shells
power
become
remains to
seeds.
feed any jet
The
base,
expanding fronts of
because the
these
balance
supernova
between
remnants
coronal
ignite
heating,
new
reflection and
rounds of star
outflow is struck
formation.
in the same compact volume. Across the population of high-mass X-ray binaries, differences in spin and inner radius would therefore translate into differences in the hardness and variability of the illumination they cast onto the galactic plane. With the innermost stable orbit fixed and the role of spin setting efficiency and timing established, The narrator stands
The
at the
dampening
final
field held
threshold
stable
where
at
stable
500
orbits end
GRC.
and motion
Radiation
becomes an
scrubbers
inward fall,
performed optimally.
where the absence
Data
of a surface
acquisition is
becomes
complete.
more than a concept and turns observable through what fails to appear. The path remains strictly inward to the horizon's domain, and to the tests that separate a compact star
Brightness
with a hard
is
crust
not
from an object that
nearness.
hides its interior behind a boundary from which light cannot return. The narrator now crosses the final annulus of stable motion and considers the boundary that does not shine the line beyond which matter and light no longer return. In an ordinary star-infalling gas strikes, a surface converts kinetic energy to heat in a boundary layer and radiates a bright flare that betrays the presence of a crust. In this system, no such boundary layer is seen. Instead, as gas approaches the inner edge of the disk, much of the remaining gravitational energy is released in the rings just outside the last stable orbit, and in the tenuous hot corona above them.
The quiet
Inside the edge,
geometry
the
of a
flow
spiral.
plunges and carries what heat remains across a horizon that does not radiate.
Where density
The absence of a
becomes
surface has
light.
observational consequences. There are no sudden thermonuclear bursts from accumulated fuel on a hard crust, no pulses tied to a persistent hotspot rotating on a stellar body, and no extra glow at very low accretion rates from matter that trickles down and must eventually strike a wall. What is seen instead is a steady high-energy source, whose spectrum and timing are set by a disk, a corona, and a weak jet with luminosity that tracks the supply from the wind and not the episodic ignition of a surface. A consensus point at this depth is the contrast between systems that host neutron stars and those that host black holes when the inflow becomes faint. Neutron star binaries, even when dim, often reveal a soft excess or a boundary layer component that signals heat released where matter meets a surface. They can show thermonuclear
against the
flashes when
dark.
hydrogen or helium accumulates and ignites suddenly under high pressure. In wind-fed systems with supergiant donors, those flashes can be rare, but the principle holds a surface collects fuel and can light it.
And the field.
In black hole binaries, the dim state shows a different face. The spectrum remains dominated by the hard Comptonized light from a hot, optically thin flow, and the total luminosity falls to values lower than comparable neutron star
Where
systems supplied
pressure
at similar
fails,
rates.
fields
The
prevail.
simplest reading is that in the absence of a surface, a fraction of the energy that would otherwise be radiated is advected inward and lost from view through the horizon. The Eddington concept, the balance between radiation pressure and gravity in a spherically symmetric flow, offers another angle on limits. In a disk, geometry and scattering change details, but the idea remains there is a scale of luminosity at which radiation strongly pushes back. In neutron stars near this scale, radiation couples to the surface and can drive photospheric expansion during bursts, a visible diagnostic event. In this system, the luminosity reaches fractions of that limit during bright intervals without any signature of a surface reacting to the push. The inner disk puffs, and the corona strengthens or weakens, but no expanding photosphere appears consistent with
From
the
the ashes of
interpretation that
stellar
the
death
deepest
come the
boundary
seeds of
is not a
rebirth.
radiating
These
crust,
heavy
but a horizon. Energy accounting at the innermost radii also reflects the absence of a solid stopping point. In a
The
surface
dispersal
bearing the
of
object,
clusters.
even if the
Watch
disk
how open
truncates matter,
clusters dissolve
that
and
leaves
scatter,
the disk
leaving
must
faint
still
traces
deposit
of
its
their
residual
origin.
kinetic energy at the boundary. In a horizon-bearing object, matter can carry a portion of that energy inward without leaving a radiative trace. Models that match the hard-low luminosity spectra in such systems invoke flows in which ions remain hotter than electrons, and in which a significant fraction of the heat is not
gas
efficiently
rotates.
radiated before the gas crosses the horizon. When the supply rises and the thin disk returns to the last stable orbit, radiative efficiency grows and the spectrum softens, yet still there is no added surface glow. The light emerges entirely from the orbiting rings and from the hot scattering medium above them. A lesser-known detail relevant here concerns the behaviour of polarisation from the very inner regions. In a surface-bearing object with a bright boundary layer scattering near the surface can produce a polarisation signature that varies with energy and that aligns with the stellar geometry. In a horizon-bearing object, the dominant polarised signal at high energies is expected to arise from scattering in the coronal volume and from reflection in the innermost disk, with angles that track the disk plane rather than a stellar surface.
Energy in translation.
Preliminary constraints
Trace
in
the journey
comparable
of starlight
systems show
as it
patterns
becomes
consistent
heat,
with disk
turbulence,
and coronal
shadow.
scattering, and with general relativistic rotation of the polarisation angle near the black hole, not with a bright rotating belt on a crust. Although current measurements for this system are limited, the expectation from geometry aligns with what is seen. Polarisation when detected is low and tied to the disk orientation, not to a surface hotspot. The time domain offers parallel clues. In neutron star binaries, coherent or nearly coherent pulsations can appear when accretion is guided by magnetic fields to small regions on a surface. In this system, no coherent pulsations persist across long intervals. Variability is strong, but it is broadband flicker and weak drifting peaks that trace dynamics in a disk and chrononautsics umbra, steady lighthouse beams from a spinning surface. At the fastest timescales accessible to current instruments, variations reflect compact coronal zones and reverberation echoes rather than surface oscillations or crustal modes. The lack of coherent rotational signals is not by itself decisive because some
The dust
neutron
acts as a
stars
filter,
do not pulse
scattering
strongly,
the blue starlight
but
and allowing
combined
the
with the
warmer
spectral
tones to
behaviour,
dominate,
the absence of
causing the
bursts and the reflection geometry, it supports the horizon interpretation. The flow inside the last stable orbit sets the
By
strictest
utilizing the
test.
hue,
If
position,
that
and
region
spectrum data
radiated
from these maps
efficiently,
of color
one would
and
expect
motion,
a tail of
we
light
uncover the
shaped by
universe's
extreme
hidden
redshift, and by the
architecture.
focusing of photons along bent paths, a distinct additional component beyond reflection that traces dissipation in plunge. The observed spectra in soft intervals can be
spiral
fit
beneath
without
the
invoking
cross.
such extra radiation. Reflection modelling
There, the
thermal
foreground
continuum
dust layer
fits
is
and timing
separating
lags
cleanly
close
now.
the energy budget with
And
a
the
disk that
velocity data
extends to the
confirms the
last
shift
stable
in the
orbit,
CO
a
emission.
compact corona, and modest
Parallax
returning
provides the
radiation.
first rung on the
Any
cosmic
added
distance
light
ladder.
from the plunging region
But to
must be
measure the
small.
truly immeasurable,
This weakness
we
is natural if the flow quickly loses its ability to radiate and carries its energy inward. It would be unnatural if a surface sat
Windows
close
across
below,
wavelengths.
because then even a weakly
visible
radiating
light to
plunge
the
would
pulsing
deposit
energy
energy
of
on
radio
impact and
waves,
force a
the
surface
heat
glow.
signatures of
An
infrared.
unresolved mystery
Follow
remains
the
how close to
21
perfect
centimeter
darkness the
line as it
horizon's
divides the
neighbourhood is
sky
in
into
practice.
layers of moving gas.
Magnetic fields do not vanish at the edge,
Molecules in the
and
cold
simulations
reveal
show
how
that
carbon
stresses can
monoxide
persist
marks
a
the
little inside
birthplaces
the
of
last
new
stable
stars
orbit.
within hidden
Some
filaments.
dissipation could occur in this plunging layer. If so, the light it makes would be strongly redshifted and smeared, and would blend with the reddest wing of the reflection spectrum. Distinguishing such a contribution from the combined effects of high-density
This
reflection
high-temperature map
and
shows
returning
how X-rays
radiation
chart the immense
requires
energy of
higher
stellar
precision
explosions
than
and
present
the powerful
measurements
pull
allow.
of gravity combined.
Another open question is whether faint radiation-driven winds from the innermost disk contribute a thin veil of scattering material that could mimic a weak surface component by adding soft delayed light. Current data favour a picture dominated by disk corona and
Deneb.
reflection, but a small
luminous
contribution
anchor.
from an inner breeze cannot yet be excluded. The donor's wind adds complexity to these tests by absorbing and scattering soft photons along certain lines of sight. Orbital phase changes the column density and the path, and that modulation can mask or reveal subtle features near the ion band and at the soft end of the spectrum.
These invisible
Careful
magnetic
phase
threads
resolved
channel the diffuse
spectroscopy
gas,
mitigates
shaping
this.
its slow
And when
collapse.
spectra are sorted by
Radiation
phase, the
hard
same
and soft.
conclusion emerges: a
Contrast
reflector
the
at the
harsh
last stable
ultraviolet
orbit,
of
a
young
compact
clusters with
coronal
the gentler
source,
glow
no boundary
between them.
layer, and no
Depth
bursts.
of ionization.
The phase behavior itself
This
helps
is how
absorption,
radiation
hardens the
sculpts
spectrum
the
at
edges of
predictable
molecular
phases,
clouds.
as the line of sight cuts through the denser wake, whereas a surface would shine regardless of that geometry. From a larger standpoint, the absence of a surface shapes how the system returns energy to its surroundings. Without a crust to re-radiate at low accretion rates, the quiescent state becomes fainter and harder than in comparable neutron star systems, reducing the long-term baseline
Where
heating of the
shells
local
become
medium.
seeds.
When
The
accretion
expanding fronts of
brightens,
these
the efficient
supernova
inner
remnants
disk and
ignite
corona
new
deliver
rounds of
hard
star
photons
formation.
with high penetrating power that reach diffuse gas well beyond the binary. Integrated over many system horizon-bearing sources, weight the high-energy tail of the interstellar radiation field more strongly than surface-bearing sources of similar supply. The difference is subtle in any one neighborhood, but accumulates across the
The
plane.
dampening field
The
held stable at
horizon's
500
defining
GRC.
property that it
Radiation
hides.
scrubbers
Whatever
performed
crosses it
optimally.
leaves one
Data
more
acquisition is
observational mark.
complete.
Light curves do not show the echoes one would expect from a bright inner surface reprocessing coronal flashes. Instead, the only echoes seen are the
Brightness
short reverberation
is not
lags from the
nearness.
disk skin, consistent with the mirror that ends at the last stable orbit. Were there a surface, one would expect an additional slightly longer lag associated with light that reaches and returns from a radius smaller than the inner disk. No such lag stands out. The delays remain short and fix both heights and radii in a geometry that ends at the edge of stable orbits. On planetary scales, this boundary that does
Faint
not shine
filaments
influences
aligned
how
with
many hard
magnetic
photons
fields.
escape each system for a given mass
Echoes of
supply. High spin and a horizon together raise radiative efficiency in the disk, while preventing any surface from adding a cool thermalized component.
Quiet geometry.
The result
of
is a
spiral.
harder, more penetrating output that affects chemistry in diffuse clouds and keeps certain
Where
ions in
density
higher charge states in
becomes
regions far from young star clusters. The jet, when present, adds a thin thread of momentum and magnetic field, but the dominant export is radiation shaped by a disk that reaches close to the last stable orbit, and by a corona that sits only light seconds above it. With the nature of the inner boundary read through absent signatures as much as through present ones, the narrator reaches the innermost station on the inward path. The next and final step looks outward again, not to introduce another region, but to gather the methods by which these conclusions are tied to data across wavelengths and time, the ensemble of timing, spectroscopy, imaging and astrometry that fixes masses, distances, spins and flows, and the uncertainties that remain where models and measurements meet. The narrator now steps outward just enough to show how the
Starlight
portrait of this
against the
system is
dark.
assembled from measurements across wavelengths and time, because every claim about mass, spin, distance, flow and boundary rests on methods that convert light into geometry. The foundation is the
filament
orbit traced by the
and the
luminous
field.
supergiant. High-resolution optical spectroscopy measures the periodic shift of absorption lines as the star moves around the center of mass. From the period and the amplitude of that shift, the mass function emerges a compact relation that sets
Where
a lower
pressure
bound on the
fails,
mass of the unseen
fields
companion.
prevail.
On its own, the bound is not decisive because inclination and the mass of the donor remain to be fixed, but it sharply limits possibilities. Photometry then finds a gentle repeating brightening and dimming. Over the same period, a pattern caused by the star's tidal distortion into a slightly elongated shape. This ellipsoidal modulation ties the inclination and the size of the star relative to the orbit, and when the absence of full X-ray eclipses is added, the allowed inclinations narrow further. Together, these constraints push the unseen mass above the maximum allowed for a neutron star and into the black hole regime. The distance is measured directly by parallax. The star's position on the sky shifts with Earth's orbit by a small angle that translates into a finite range along the line of sight. At radio wavelengths, very long baseline interferometry resolves a
From the
compact
ashes
core
of
near the
stellar
X-ray
death
position
come the seeds
and
of
measures
rebirth.
an independent
These
parallax
heavy
and proper motion when the source is bright enough. Optical and radio distances agree locking the system scale, and
The
letting
dispersal of
luminosities be
clusters.
computed without
Watch how open
model-dependent
clusters
guesses.
dissolve and
X-rays
scatter,
add the fast
leaving
clock.
faint traces of
Instruments
their
with
origin.
large collecting area record light curves with sub-second resolution, revealing broad flicker and narrow drifting peaks that encode the size and dynamics of the emitting region. Spectra taken at the same time show a soft thermal component from the inner disk and a hard tail from the corona,
This is the dance of
fitting
angular
the soft
momentum.
component with the models of thin,
gas rotates.
optically thick disks yields an inner radius that during brighter and softer intervals sits very close to the innermost stable orbit for a rapidly spinning black hole. Fitting the hardtail with Comptonization models yields electron temperatures and optical depths that track state, and the cutoffs shift with the balance between coronal heating and cooling by soft photons. Phase-resolved X-ray spectroscopy across the orbit maps changing absorption as the line of sight crosses the focused wind and wake, isolating the system's own variations from foreground dimming. High-energy timing then measures reverberation. Hard photons hit the disk, and after a light travel delay the reflection appears. The delay varies with energy because each part of the reflection spectrum forms at a slightly different depth and radius. These short echoes place the coronal source only
Energy
a few
in
gravitational radii above the
Trace the
axis,
journey of
and
starlight
anchor the
as it
reflector at
becomes
radii
heat,
consistent with the
turbulence,
soft
and
component
shadow.
fits, providing a cross-check between independent methods. Reflection itself acts as a ruler and a clock. The ion complex, broadened and skewed by Doppler motion and gravitational redshift, ties the inner edge of the reflector to a radius near the theoretical limit for prograde orbits in high spin. The Compton hump, a broad rise at higher energies, sets the reflection fraction and the ionization state of the surface. As the spectrum hardens, the ion profile strengthens and the emissivity steepens, consistent with the lower, more compact coronal source and stronger light bending. As the spectrum softens, the blurring eases slightly and lag shorten. These coordinated shifts map geometry changes without requiring assumptions about unknown beaming patterns. At softer energies, subtle excess emission below the ion band implies high densities in the surface layers, and models that include such densities bring fits into closer agreement without resorting to unusual compositions. Across many intervals and phases, the same message repeats: a thin disk that extends to the last stable orbit. A compact coronal
The
source,
dust acts as a
whose
filter,
height varies
scattering
within a
the blue
narrow
starlight
range
and
and
allowing the
reflection
warmer
that
tones to
samples
dominate,
curved spacetime
causing the
directly. Radio observations fix the outflow. A compact, flat spectrum core brightens when the spectrum is
By
hard and
utilizing the
fades when it
hue,
is soft.
position, and spectrum
The
data
core
from these
position
maps of color
shifts
and
with
motion,
observing
we
frequency
uncover the
because the jet
universe's
becomes
hidden
optically
architecture.
thin, farther from the engine at lower frequencies. A textbook core shift that encodes magnetic field and particle density gradients along the flow.
The spiral
Weak stable
beneath the
polarization aligns with the core axis after correcting for Faraday
There, the
rotation in the
foreground dust
ionized
layer
wind,
is separating
tying the
cleanly
jet
now.
to the disk plane
And the
set by the
velocity
optical
data confirms the
constraints.
shift in the CO
Orbital
emission.
modulation of low-frequency
Parallax
radio
provides the
flux
first
by
rung in the
free
cosmic
absorption in
distance
the
ladder.
donor's wind
But to measure the
confirms
truly
that the outflow
immeasurable,
threads a
we
dense environment, and that the binary geometry influences even the most extended structures close to the engine. Occasionally,
Windows
at higher
across
frequencies,
wavelengths,
the spectrum
from
steepens
visible
where the
light
jet
to the
becomes
pulsing
optically
energy of
thin,
radio waves,
and that break
the heat
shifts with
signatures
state
of
marking
infrared.
changes in conditions at
Follow
the
the
base.
21
Ultraviolet
centimeter line
lines
as it
trace the
divides
wind
the
and its
sky
feedback.
into layers of
P
moving
Cygni
gas.
profiles reveal outflow speeds of
Molecules
thousands
in
of
the
kilometers
cold
per
reveal how
second and show
carbon
how
monoxide marks
ionization
the
by the
birthplaces
X-ray
of new
source
stars
alters
within hidden
acceleration on the
filaments.
starward side of the orbit. Narrow phase-dependent absorption features from highly ionized species mark the focused wake and move with it, offering a direct probe of the velocity field in the stream that feeds accretion. In the infrared, the donor's
This
photosphere
high-temperature map
dominates, yet
shows how
careful
X-rays chart
subtraction
the immense
reveals
energy of
small
stellar
variable
explosions and the
components
powerful
tied to the
pull of
accretion
gravity
flow
combined.
and sometimes to the inner jet. Across all bands, the multi-wavelength picture is coherent geometry set by optical and astrometric anchors, fast high-energy behavior set by disk corona and reflection, outflow tied to hard states, and wind signatures
Deneb.
that both feed and
The
modulate
luminous
accretion.
anchor.
Uncertainties remain and define the frontier. The black hole's spin is inferred from the location of the inner disk edge and from the breadth of the reflection features. Both methods rely on models that assume a thin disk, small stress inside the innermost stable orbit, and a particular coronal geometry. Systematics in those
These
assumptions
invisible
map
magnetic
into
threads
ranges
channel
on
the
spin.
diffuse gas,
Current
shaping
fits
its slow
favour very
collapse.
rapid rotation,
Radiation
but
hard
whether the
and
value
soft.
lies just below the
Contrast the
theoretical
harsh
maximum
ultraviolet
or a
of young
small
clusters
step
with
farther
the
out
gentler
depends
glow
on
between
details
them.
of density and the surface, the
of
fraction of
ionization.
returning radiation, and the
This
exact
is how
height and
radiation
compactness of the
sculpts
coronal
edges of
source.
molecular clouds.
The wind's clumpiness is another open parameter. Clump size, density, contrast, and distribution control the variability of the capture rate and the amplitude of absorption dips. High cadence phase resolved ultraviolet and soft X-ray spectroscopy continues to refine these properties, but degeneracies between ionization geometry and column density persist.
Where shells
The topology of the
become
corona and the link to
The
the jet
expanding
remain
fronts
live
of these
questions. Is
supernova
the heating a
remnants
single
ignite
compact
new
lamp
rounds
or
of
a
star
swarm of
formation.
short-lived patches? Does the jet base tap the black hole's rotational energy or only the inner disk? How much magnetic flux accumulates near the axis in a wind-fed system? And how do these conditions drift over years as the donor evolves? Answering these requires simultaneous timing spectroscopy and polarimetry that are only now becoming routine. Population
Dampening field
context
held
helps
stable at
place this
500
system in
GRC.
a wider frame.
Radiation scrubbers
High
performed
mass X-ray
optimally.
binaries
Data
with
acquisition
wind-fed
is
accretion
complete.
are common along spiral arms where massive stars are young. Most host neutron stars. A minority host black holes. Among black hole systems, few are as
Brightness
persistently bright
is
and as
not
well measured as
nearness.
this one. The combination of a luminous donor, a tight orbit, a steady wind supply, and a high spin makes it a reference case for testing methods that read gravity from light. It also constrains models of binary evolution. The mass of the black hole, the modest orbital eccentricity, and the motion of the system through the galaxy together suggest a collapse with little asymmetric kick, a path that informs how often
Faint
massive
filaments
stars end as
aligned with
black
magnetic
holes
fields.
without bright supernovae.
Echoes of
Long-term monitoring of the star's spectrum will test for secular changes in wind strength and rotation as the donor evolves, changes that could alter the accretion
quiet
rate,
geometry
the coronal
of
power
a
split,
spiral.
and the jet's faint thread. The planetary scale observation closes the loop. A single compact engine embedded in a rich star field adds a persistent stripe of hard light to the interstellar radiation field spikes local ionization fractions along certain sightlines and stirs the nearby medium through weak outflows. Many such engines distributed along the plane contribute a background that shapes chemistry and temperature in diffuse clouds far from clusters. Their efficiency depends on spin because the last stable orbit sets how much of the captured mass turns to light before it disappears. So a distribution of spins becomes a distribution of high energy output at the scale of the galaxy. Measurements in this system therefore reach beyond one binary. They anchor how a class of sources injects energy into the disk. The narrator maintains the rules of the path. The account stays in third person, present tense, calm and steady,
Starlight
anchored in
against the
consensus
dark.
and bounded by uncertainty where models meet limits of data. The inward journey has moved from the galactic disk to the Cygnus window, from the outer spiral to clustered
The
birth, from
filament
binary
and
evolution
the field.
to wind capture, from circularization to a thin disk, from hot corona to reflection in curved space-time, from jet coupling to the last stable orbit, and from the silence of the horizon to the methods that make
Where
silence
pressure
teachable.
fails,
The
fields
outward look
prevail.
remains only a momentary adjustment to show how measurements assemble a coherent picture without foreshadowing beyond the present scope. With the observational ledger in place and the open questions mark the sequence of regions is complete, the narrator lets the scene settle into quiet. The galaxy turns with unhurried grace and, along one arm, the window of Cygnus remains crowded and bright. The binary at its center of attention continues its steady exchange. The supergiant breathes a fast wind. The unseen companion gathers a fraction of that breath, shapes it into a thin disk, warms a hot, tenuous corona, and returns much of the borrowed energy as high-energy light. Reflection from the inner rings carries the imprint of curved space-time. A faint jet threads away along a stable axis and fades into the surrounding medium. Nothing breaks the calm. There is no surface to flash or flare on contact. Variability remains a soft flicker carried by the flow and by the small shifts of geometry that modulate light. Around the system, the interstellar medium accepts the radiation without haste. Ionization fronts hold in place inside the cavities carved by clusters. Dust dims and reddens the starfields, and the long sightline keeps its layers. Far above the plane, the halo drifts. Far below it, the inner ring of the galaxy turns. The same equations that govern this one disk recur at other masses and scales, and these same balances between pressure, gravity, radiation, and magnetic fields appear in other settings with different tempos. Here the tempo is measured in orbits of days and in light echoes that cross in moments. The signatures remain clear enough to read mass spin and distance with modest doubt and steady method. In the time it takes the pair to complete another circuit, nothing essential changes. Gas continues inward. Heat becomes light. Light crosses the wake, the wind the arm, and the quiet thickness of the disk, and a small share of it reaches distant clouds that hold its trace. The narrator does not search for meaning. The account ends where the regions end at the edge of the last stable ring, and the boundary that does not shine, with the system continuing its patient exchange in the wide, slow turn of the galaxy.